Test, Test. Ich habe das mal gesehen. So, test. This should be a bit delayed now. It's going to come in a second. It's a bit delayed because the stream is always behind a couple of seconds. So the moment you see me away from there, so test. There you go.
Perfect. Done. Screen continues. Audio is okay.
Yep. The central left, was it?
People are asking if there's a PDF of the presentation.
Later.
Later. Okay.
Ja. Ja, wir fangen jetzt, wir starten now. Wir fangen jetzt an. Ja, wir sind schon online. Hello everybody, welcome to our Reinforcement Learning Bootcamp. So we are all very excited. You see here the organizers on the stage, not all. Olga will come in a second. And we are really happy that you're here. So I will just open some slides. And also welcome to the online audience. Thank you. Thank you, Marius. So we just prepared a few slides and we want to keep it easy for the opening. It's more about exchanging among each other in this bootcamp. And this is just a short outline of what you can expect in the next 30 minutes, which is we will introduce ourselves, we will tell you why we are doing this, what can you expect, what are our goals for this, some logistics and housekeeping on the social events, and if you need help, who to ask. So, let's start with setting the context of this workshop. So, it was a small idea a few months ago. Catherine and me had during our reinforcement learning coffees. I will find some words about this in a second. So we said, okay, it would be really nice to have a boot camp in Austria, to somehow engage the community, to bring people together, to create a movement. And now, I mean, we are almost full in this hall, so I'm really excited to see so many people here. We did not expect this. It was expected to have 25 people. Now we are more than 70 here. This is great. So really, we are really happy to have this. And the Reinforcement Learning Coffee is just an informal meeting we do every first Friday of the month, which is really an easy environment to exchange ideas about reinforcement learning. So it's very informal and very small discussions we have. People present their problems, and this was taken over from something which turned out to be very successful at CERN. I started to do machine learning at CERN, and there, in the beginning, we saw that there's great potential in using optimization machine learning to control the accelerators there. And nobody had a clue, so we just met for informal machine learning coffees. And we gave us lectures there, and this created a strong movement, which now is established. So this is a great way to engage research, in my opinion. That's the Reinforcement Learning Coffee. If you want to participate, just let us know. We will send out a link, and you can just put in your email, and you receive news about that. So Catherine and me are usually moderating this, and yeah, it's cool. So the main idea is to strengthen the RL community. This is why we are doing this workshop, as I said. And it should be done in Austria to create more movement in artificial intelligence here, but we are international, so this goes beyond Austria by far. And just one thing which is really important, we did this event for free. So we took our fundings, we will see all participants in a second, and we offer this for free. So this was a lot of effort, but we are happy that we made it happen. But this is not falling from trees. This is what I want to tell you. So thanks for being here. All right. Since I talked so much already, I would say that people start to introduce themselves, and I will be the final one. So I hand over to Catherine now, please.
Perfect. Thanks, Simon. From my side, my name is Catherine. I'm from Fraunhofer, Austria. I'm also really happy to see you all here. Thanks, everyone, for coming. Like I said, this idea was born a long time ago. It's a lot of effort to get something like this off the ground. But I think the point is, and this is something also for like my colleagues at AI Austria, a lot of us realized we were at our companies alone. We were going online on YouTube and reading Sutton's book alone and trying to figure out what reinforcement learning was and how it works. Then we started talking to each other and realized, like, okay, we're all just doing the same thing. We're trying to teach ourselves this. And especially from my side, I miss the kind of collaboration atmosphere that a lot of us maybe know from our like academic times. And we're trying to bring that back into this field of reinforcement learning. So the point of this workshop, or this bootcamp, we're all kind of learning this stuff together. We can profit from experience from each other, and it's nice to have kind of people around to learn it with. So that's what I hope you guys get from this, is not just kind of the information we'll get. We have some great speakers talking from their experience, but also the other people around you. You can, then talk about the problems you're working on, maybe hear what they're doing. I think that's also really, really valuable. Now I forget my own introduction. So yeah, I'm at Fraunhofer. I've been working in reinforcement learning for 5 years now. But like I said, it was self-taught out of my own interest. My background's in physics also, like many of us, I think, actually. And I was working on quantum computers, and then started working more on AI topics when I started working at Fraunhofer, because it's a lot more practical. It's really working with companies directly, and that's where AI came in. So I will pass along the torch. Thomas?
Perfect. Yeah, hi everyone. My name is Thomas. I'm a researcher at IONIM Research Institute for Robotics. And I got first in touch with reinforcement learning, I guess, 5 years ago when I met Andreas here on the left side. And that's basically was also kickstarting this whole idea of having a community, because it's very, I would say, I'm pretty overwhelmed to see that so many people are interested in the field, and it starts to really, elaborate over time. Yeah, apart from that, not so much to say about me, so I will hand over to one of you guys. You can. I'll pass it to you. Yes.
Okay. Yeah. So, hi everyone. I'm Mario Estino. Represent a bit from Johannes Kepler University. Doing my PhD. Couple of reinforcement learning papers if you want, so in offline reinforcement learning, a bit related also to continual learning. So I've had some, let's say, traits on that part. Meanwhile, I represent the company Extensity AI, own startup that focuses also in part on reinforcement learning, also in neurosymbolic systems. And it's really cool to see how these things now come together, and how we can basically leverage algorithms from reinforcement learning and mainstream this idea of how to basically optimize and tune even large language models, as many of you might know, or any kinds of other optimization tasks in neurosymbolic systems. Thank you. Now I pass on to you.
Great. Well, very warm welcome also from my side, also on behalf of the organizations I represent, which is AI Austria and IONIM Research. Like Catherine and like many of us, I'm a theoretical particle physicist and got into reinforcement learning because it's a very exciting technology, as I'm sure you're aware of. I'm very happy to be part of this group here. Like, as you see, Catherine is a central node here among those people, and truly she is, because that is like how I got into like being more involved with a community building effort for reinforcement learning when we met, like, I think it was 5 years ago in Vienna, and we figured out that it would be great to have, like, a community where really you can discuss in-depth questions about deep reinforcement learning. I wish you a really great workshop. Use this opportunity, talk with those amazing people here. We have an amazing lineup of really, really great speakers to which I'm really looking forward to, and discuss with each other. Really use this as an opportunity, and yeah, I'm very happy to be here. Big shout out also to you, Simon, Olga, and Sabrina, who is not here, for organizing this thing. Really, really great. And Olga, please, go ahead.
Hi everyone, I'm Olga. I'm pursuing my master's degree in data science in the University of Salzburg. and I also work with Simon with some reinforcement learning projects. Yeah, and of course I would like to write my master thesis in the reinforcement learning area. So that's my bio.
Thanks, Olga. So, well, my name is Juan Manuel Montoya Vallardo. You don't need to remember the whole name. I'm not here because I just jump in to help Simon right now. So if you have some questions like about where to go or so on, just please ask me. I'm doing my PhD with Christian Borgel, which is there, Heid, and Simon. And my topic is reinforcement learning and right now also control theory for nautic robotics. So I'm pleased to help you out. Thanks.
Thanks, Juan. So now, finally, I'm again on the stage. So I'm Simon Hilender. I try to establish a reinforcement learning team here in Salzburg. I'm part of the IDA lab, which is a lab which tries to collaborate with local companies or with companies in general to generate some fundings. And we provide research on data science and artificial intelligence to improve the products of companies. Yeah? So this is challenging. It's a challenging thing, and this is why I'm really happy that we have several companies here today. So I hope that this is engaging, and this brings me to the next slide. But just one thing, Sabrina is unfortunately not here. She got sick, but she's also part of the organization team. She does her PhD in multi-reinforcement learning in network communication. Okay, so why are we doing this? First of all, of course, because it's fun. So we all love reinforcement learning, I would say, and we have a lot of fun. And so we should also have a lot of fun here the next days in learning to know reinforcement learning a bit better, but also maybe to bring reinforcement learning from the academic field more to a practical field, because reinforcement learning still is a really tricky subject. And I saw this here. I tried to convince companies they might use reinforcement learning, but it's really hard to make a point with reinforcement learning. And maybe this helps a bit to get this on the road, right? Because reinforcement learning has a huge potential. Of course, we want to improve their communication between research and the community, between research and society, between research and companies. Because we are sitting in our offices, we develop cool tools, and we want to somehow have an exchange with society. This is also a reason why we are here, because this is a tricky business. And also make the research efforts we are doing in our offices more visible. So we are many different companies, like Catherine is from Fraunhofer, then we have Andreas and Thomas and Marius from AI Austria, then we try to have the SAL team. SAL stands for Smart Analytics, which brings the money, and reinforcement learning, which is the fun part, let's say, right? And also Marius has his own Extensity AI company. So yeah, that's us, that's the last slide on this. Now, what can you expect? And of course, this should be a dialogue. This is a boot camp. So boot camp is that we all learn something here. It's not a conference where we show off. It's more to communicate. Yeah? So we want to connect with enthusiasts and researchers more deeply in reinforcement learning, to share our experience. So we all went through painful phases in our reinforcement learning life, and this is some sort of therapy we can do together, because it can take a lot of effort, especially when you're doing your PhD in reinforcement learning. This is really hard, as Juan could tell you. Yeah, we want to teach you fundamental concepts of reinforcement learning, if possible. Yeah, so also to show you some practical applications. We discuss general challenges of reinforcement learning, and hopefully we bring together the field a bit forward. This is the thing which is needed. We need a momentum in science that things develop, that things get better. because this is done by research, this is done by people, and this is the only way, in a collaborative way, you can bring science forward, and especially reinforcement learning. Yeah, yeah, and hopefully, communists, please engage. We want to engage you to do research and work with us. So, some logistics and housekeeping. The timetable is online. You all have it, I hope, and I think we have some printed versions around. Maybe shall we go through it? Okay, lunch is always at 12:30 in the Mensa. The program starts at 9:30 tomorrow and on Friday as well. And we end usually at 18:30 somehow. Let's see how it goes. Because every day ends with a hands-on session, and of course if we have good discussions or so, it will go on maybe. An important aspect is that the workshop is recorded, so we are online, and if anybody disagrees with this, you should tell us now. Also, you're not visible. You will be. Also, we take then a group picture right afterwards. Yeah. at Raswan's talk. So if you don't want to be, because we will share this picture online, then you should not be on the picture, please. The tutorial is a technical aspect. We need around 5 gigabytes of space if you didn't install it yet. So who wants to participate and didn't install the stuff? Oh, it's just one person. Very good. No, this is good because otherwise the bandwidth breaks down. And also, yeah, because we lost some time in the past. Also, we don't. Okay, sorry. Also, there's an update on the requirements, so please run it again. It just installs some additional packages. It should go very quickly, I hope. But for the first part of the tutorial, we need this. So we have 2 parts, one today, which is given by Thomas, and one tomorrow, which is given by me. So there was an update on this. And if you need any assistance, please let us know. Yeah, this I said already. Okay, the social events. We are going out for dinner in the evening. That's all concerning the social events, today and tomorrow. And we decided to have 2 groups, which is, one group is walking into the city, so it's walkable distance. I don't know how long does it take approximately to walk there, 30 minutes or something?
No, it was
40 minutes.
Yeah,
So,
maybe
okay.
we can take a bus to the center.
Exactly. Or you can take, if you don't want to walk, you can take the bus, of course. So you
But the
will.
bus is 20 minutes.
Yeah, okay, thanks.
So
Great.
you can make some exercise, just 20 minutes more.
So the dinner starts at 19:15 at the Cirkelwirt, and the details are online. We have some registrations. We had a form sent out who wants to participate. If you didn't sign up and you want to participate, please let us know, maybe not, as soon as possible, that we can rearrange the reservation. Yeah, if there are too many. So we have some uncertainty, but let's see. So, but I encourage you to join, of course. There are always nice discussions after the work is done. Tomorrow we have also dinner at Die Weiße, which is also on the webpage. You find it easily. So this was already emphasized by Andreas. It's an encouragement. So don't be shy, because we are all more or less beginners. Although we did a lot of research, still there are so many open questions. And you just make progress if you interact with people. This is how research goes usually. So take advantage of this opportunity. Also to get a good network in reinforcement learning. Especially if you're doing your PhD, it's always good to have many people to ask, right? We have really great experts, world-leading experts in the field, so take the chance maybe to grab them and discuss. We have concentrated RL superpower here. So this is really cool. yeah, we have tutorials to stimulate ideas, to get you discussing about these things. And if you need any help, so all of us can be asked at any time, especially local people. Olga is one of the, she had the most work in organizing, I would say. She did all the bookings, she booked the room, and so I would say thanks, Olga, here at this moment for your great support for making this happen. But also, Juan is familiar here with local things, and of course I am. But then you can ask all of us if anything is needed, okay? And don't hesitate to ask questions. Yeah, and many thanks to everybody who is involved in making this happen. Anybody of us, and also you, will be part of this. So I would say also thanks to everybody. And that's it from our official side, I would say, for the beginning. And now we are good on time. We have some margin to ask you a few questions. Maybe I'm interested in who is coming from research in this audience. Maybe raise your hands that we get an idea. So 2/3 maybe, I would say, right? Who is coming from company? 1/3. Cool. Yeah, and in the middle. Raswan is in the middle. Some of us are in the middle. This is very interesting. Yeah. So is there any input from your side? Any questions at this point? Anything you want to know? This should warm up a bit. This should break the ice. So let's hope that we don't have this frontal situation all the time, that we start to communicate. I hand maybe over to you if you have something to say.
I think that's everything from my side. Another big thank you to the speakers we have today.
Yes,
so one
thanks.
big aspect of this is the speakers. Maybe we can give a brief.
Yes, thanks a lot. We have 4 great
Yeah, so
talks.
our philosophy for this was there's the inspiration part, that's the speakers. There's we have some tutorials, that's like, let's learn the basics, let's talk about it together. And then there's the hands-on part, that's the tutorials. So we try and get a little bit of a balance of everything. You can have a taste of everything. We don't have that much time, we just have 3 days, but I think we can do a lot. So I think that's everything.
That's everything, yeah?
Then let's hand over to our first keynote.
Yes, we can. Welcome.
Thank you. Yeah, sorry. Let me just quickly put in the slides. So our first speaker is going to be Razvan Pascano. He is well known, I would say, in the reinforcement learning community. For years, he worked on many topics, specifically also with DeepMind in his backing, basically. He organizes also every year this Eastern European Summer School, which is an amazing place to meet him. He's also organizer of COLAS, basically. I think this year was the 3rd installment, and will be many more, hopefully, and has obviously shifted the needle a lot in our field. So please welcome everyone, Razvan, and I will just quickly put on the slides. Give it a applause, please. Here it is. And now so let me put it over. So, oops. Sorry for that.
That the sound of leap is low.
Yeah, I know. I'm just trying to figure out how we do this best. View full screen. Great. And here's the presenter, and if I may wire you up quickly.
Sure. Yeah.
If this works here.
And then, yeah, maybe.
Exactly here, I would say.
Okay, perfect. Cool. Okay, perfect. Okay, thank you so much for having me. yeah, this sounds like a really exciting event, and I agree with what everyone said, that should take the opportunity and talk. So as Mario said, I've been organizing the CML summer schools, and one thing that I find is that, you know, when people are trying to build networks, they always look up, and they're trying to build sort of this asymmetric kind of relationships with people that are in different positions. But I think the place where you gain most is like networking with people around you that are in a similar situation, because they will face the same kind of problems. They will have the time to discuss things. So I think definitely do not ignore that element. So it's not just about, I know, talking with the organizers or so on, but also talking among yourselves and getting to know each other and building that network that you can rely on each other and help each other in the project that you're building. So I'm not sure how the talk will go. We'll see. Feel free to interrupt me through it. I wasn't exactly sure what level I should make the talk. So what I wanted to discuss, and I don't know if this is the right framing, I wanted to talk a little bit about deep reinforcement learning, which I think is somewhat different from reinforcement learning and is different from deep learning. And I wanted to sort of say that, okay, there is this thing that lives in the middle, and there's like weird interactions coming from both sides. And maybe now is not that much the case, but at least a few years back when I was playing with this a lot, in the community you typically had RL people and you had deep learning people, but you didn't have anyone in the middle, right? You had people that had formal training in RL, and for them, the neural network, maybe I can use my slides to explain this. So you know, this is the RL framework, the way, you know, typically maybe you've seen it. So this is the RL framework. You have an environment, you have an agent. The agent does actions. And then, you know, the environment gives you observations and reward. And RL, it's a lot about, okay, how do you learn within this framework, right? How do you construct updates for the agent? And sort of in the early days of deep RL, basically for the RL folks, the way they were thinking about it is, well, we're just going to use these neural networks as function approximators because they work well. But it's still an RL problem. Like what we're studying is RL. There's just sort of a choice of function approximator that doesn't play a role. And then you had deep learning persons that would say, well, we're still doing deep learning. We just changed the objective. You know, instead of doing mean square error, we're using this Q-learning update, whatever it is, and I don't care of it, and I'm just going to focus on the neural network. And I think in this talk, I want to say that, well, it doesn't work that way. That there are issues on both sides, and you can't just ignore the fact that you're doing RL, and you can't ignore the fact that you're using neural networks function approximators. I'm not sure if I'm going to manage to convince you, but we'll go through it and see if you agree. Okay, so initially it seemed trivial, but yeah, what would go wrong? So, and I'm going to start more of like weird things from deep learning that come into play when you're trying to use this in RL. I think that would be kind of 80% of the talk, and that's because I'm actually a deep learning person. So when I did this, for me, RL was just an objective, and this is sort of the kind of things I'm sort of more familiar with. And you know, I was frustrated when talking to colleagues when they were doing colleagues that are more RL based, that they would kind of just ignore these things that I thought are fundamental, and like, how can you not pay attention to this when you're doing your thing? At the end, I'm going to try to talk a little bit about the reverse as well, and see how that goes. So yeah, so this is deep learning. So okay, so what's the okay, this is a big slide. There's a lot to unpack, but what do I want to say here? So deep learning, well, neural networks in general, they're nonlinear function, and they're universal function approximators. And a lot of time, I get a sense that the way people think of neural networks is this sort of very powerful models that they can do anything, right? So you have the data. As long as you have data, you put the neural network in the middle, and it's going to train. And partially, the reason is sort of this universal approximator property that these models have, that I think is misinterpreted many times when people think about it. It doesn't really say what we think it's saying. But also, like, I think there's sort of the nonlinear property of the model. So when I'm trying to think of this family of functions, the way I think about it is, okay, if I have like an infinitely sized model, then the class of functions I can reach is all possible functions in some sense. It's not exactly true, but you know, is this big square is like, okay, I can reach anything if I would have like an infinitely large model. But then what I can do in practice, well, is because the model size is fixed, I can only reach a subset, so this would be H. So H is some fixed size model, and it can only reach this shape. But then the other thing is you have initialization that plays a crucial role. So one thing that is becoming more and more apparent is that the solution that you get on a neural network depends on the initialization, right? It's not like initial conditions that go away in a dynamical system. You know, I run into convergence and then there's no dependency on the initialization. The initialization stays there. So you have the initialization set that you have to pick, and then you have the kind of reachable functions that you can reach starting from that initialization point. And I'm going to argue that these are going to come into play in different ways when you start training these models, right? So maybe as just to kind of ground you a little bit, you know, like a lot of continual learning problems or like loss of plasticity, if you heard those kind of terms, they might come from things like this, where, you know, just because you've pre-trained on something, that gives you a new initialization set, is where you've converged. And when you try to learn something else, then you're not having access to the same kind of functions. You know, sometimes you can be in a pathological setting where you can't really learn anymore, so you're actually quite restricted, or you basically just cannot learn the same solution you'd have learned if you started from a different initial conditions. And these kind of affect things, and I think are things that people kind of ignore. So how does this work? Okay, so I'll start a little bit on the optimization side. So another big important aspect of neural networks is we think a lot about the architecture, but they only work together with the optimizer, right? And the optimizer is usually gradient descent based. So we have, you know, the previous slide was talking a bit more about expressivity and what they can represent. There was the aspect of learning there as well, because the functions you'd reach kind of depend on where you start, but they also depend on the optimizer. But, you know, there's also the optimizer. And the optimizer that we use is gradient descent. So ideally, and just sort of like a primer on gradient descent, you know, you have your neural network. You can think of it as some kind of random nonlinear function. So this is just an example of nonlinear function. And, you know, on the x-axis, you have the parameters theta, and the y, you have the loss. And what you're trying to do is to find the minimum of this loss. And I always find it useful to derive gradient descent. I don't know how many people actually do this, but I find it quite insightful. So how does gradient descent work? Well, the way it works is you don't know how to solve this nonlinear problem. You know, any way you look at it, you can't solve it. So what you do is you can say, well, I'm going to approximate my function with something that I know how to solve. And one thing that I can solve is a first order approximation. So it's a line, right? I can always approximate any curve with a line. So this will be the dotted line. And you do that by doing some kind of first order Taylor expansion. That would give you sort of the line, right? And I now know how to minimize on this line. Instead of minimizing the original loss, I'm going to minimize this approximation. The issue is that the minima is somewhere at infinity and is not informative. And the reason for that is because this approximation doesn't hold everywhere, right? It holds around the point where you've made the approximation. So therefore, you want to build a trust region around it. So you can say, like, look, I have that epsilon ball there, that pink circle. So I'm going to find the minimum of this line within that epsilon ball, because I think within that epsilon ball, the approximation will be similar enough with the function I care about that this makes sense. So you write this as a constraint optimization, where you say I'm minimizing this first order Taylor such that my delta theta is under some norm, and you can choose the norm, and you can do all kinds of fancy things, and you can all kinds of optimizers, but like that's not the point of the talk. Under some norm, I'm restricting to that, and now if you expand this out and then you use, and you try to solve this Lagrange method and so forth, you get the formula that we typically use, right? You get sort of this, the update that you're doing is you're taking a step in the opposite direction of the gradient. And that really comes from here. So yeah, I guess sort of this should give you an intuition. And then, you know, to learn, you have to do this process over and over again. So, but I think what's also kind of interesting is to think of the dynamics of this sort of gradient update and what it means. Yeah, this was sort of kind of a story that I was using to introduce continual learning as a problem, as an optimization problem. And I think one way to think about it, if you think about like what a gradient actually does, particularly if you're thinking over the examples that you have in the batch, the gradient is really asking for each parameter independently, you're asking the question, if I increase this parameter, would my loss go down or not? So that's really what the gradient is saying, right? So that comes from the limit. So you're independently, for every parameter, you're making this question and you're getting some answer. And you get some magnitude, that's important, but for now, let's ignore it. We're just thinking about the sign. That the gradient will say, and there are optimizers that do that, right? That just look at the sign of the gradients. There are quite a few of them that were quite popular at some point. So you're basically asking for every parameter, should I increase this parameter or should I decrease it? And you can actually think of this as some kind of voting mechanism, right? If I have a batch of data, for every parameter, some example will say, okay, pull it up. Some example will say, no, you have to shrink this parameter. And this creates this sort of tension, which is sort of the thing that makes learning work, right? This creates this sort of tug-of-war dynamics. This is how I used to call it in the paper. Some paper that I did not cite here, doesn't matter. So it creates this sort of tug-of-war dynamics where basically you can think of the data, you can think of the examples in sort of this linearized system. What the updates that come from this linearized system are doing is you can think of the data as just trying to pull parameters either up and down, and then kind of acting out this tug-of-war games for each parameter independently. And you converge and you reach a solution once you reach some kind of equilibrium. Once these forces on both sides become equal, and then there's, that they're going to stop there and going to work. And finding out. And this is sort of what creates sort of the continual learning problem. And I'm going to try to explain a little bit through this experiment. This is sort of an RL-specific one, and that's why I find it to be quite useful for this. But maybe I should have said this on the previous slide, so that, because I think I used the continual learning phrase, assuming you guys know what it is, but maybe I should explain a little bit. So this creates the continual learning problem. What is the continual learning problem? The continual learning problem is that if I learn, say, task 1 and 2 together, and then I remove task 1 from the equation, I say, okay, I've learned task 1 and 2, and now I want just to fine-tune on task 2, what happens is the system forgets task 1. So you have this sort of pathological behavior of the system that forgets about any part of your distribution that is not present during learning for a sufficiently long time. I mean, we do stochastic gradient descent, and you have all of those expectations, so it doesn't have to be present every update. But if somehow in expectation not all parts of the distribution are there, then you forget about the parts of the distribution that you don't see, or the tasks that you don't see. And this comes from this tug-of-war dynamics, because if you think about it, it's basically what you're saying is like, okay, you're removing one opponent in this game, and once that the opponent is removed, obviously the other ones are just going to pull the rope all the way to themselves. So there's like the only way learning works is because you have that tension. And how does this play in practice? So we had this, this is more of a thought experiment. So actually we did not run experiments on StarCraft. We ran experiments on bandits, but we use StarCraft because it sounds cool. So we are doing, I think there were some experiments on StarCraft as well, but there's this idea when we are training agents to play StarCraft is you'd want them to be able to play with all races. I don't know how many are familiar with StarCraft, but in StarCraft you have to pick between Protoss, Zerg, or Human, and then you play. And each race has, different kinds of units, so you have different kinds of strategies, and you have, the requirements are different, so you have a different policy for each of them. It's a different policy style, right? But if you want to get sort of alpha star out and be good, it needs to be able to play with any of the races, right? It's like, I think in the competitions, they randomly pick with whom you play, so, you have to be able to play with whomever whoever is being picked. So say you're trying to learn to play with Zerg and Protoss. One thing that we've noticed is when you start training with both of this, actually you're not learning to play with them, equally. You're not, like the multitask is not minimizing the loss on both cases at the same time. What happens is you actually learn to play with one of the race, like say Zerg, and after you're really good with that, you start learning how to play with Protoss. And this is somewhat random, like if you run this many times, it's a bit sort of random which is the race that you learn to play with first, but they always kind of end up in sequence rather than learning jointly and performing well on both of them. And this is sort of the ray interference is trying to explain this, and it's trying to explain this, and it's trying to argue that this is partially because of RL. So what happens in RL is that the quality of the data that you see depends on the policy that you have. So when I'm starting to train both of these agents, I'm just pressing on the keyboard randomly, that's what the agent is doing, you're not seeing anything. You're not seeing reward. You don't really have a learning signal. So if you're thinking about the learning signal, which I'm using it in sort of in a quotation marks, I'm not meaning any kind of specific quantity. We could try to formalize this, but for now we keep it at an intuitive level. So if you're thinking about this learning signal, what happens is it is extremely weak in the beginning. You start getting signal as your policy becomes better, because then you start observing things, you start seeing rewards, you start building units and so forth. And then the learning signal goes down again. And the reason it goes down at the end is because this is an optimization problem, more or less, and at convergence, the gradients vanish. So the learning signal is somehow proportional with the gradients. So when I finish learning, there's nothing to learn. There's no learning signal, right, when I'm playing quite well with one particular race. And this is fundamentally different to how things are in supervised learning. In supervised learning, you have a lot of learning signal in the beginning because you have high error, and then you don't have any learning signal at the end because you have low error. And the signal is kind of monotonically decreasing. I mean, that's how it works. And why is this important? It's important because if you have this, and you have the interference we were discussing before, so this kind of tug-of-war dynamics where, say, StarCraft wants to use the weights to do something. The Protoss wants to use the weights to do something, and the Zerg wants to use them to do something else. Then things get interesting, because what's going to happen is by chance, one of these two losses, they're going to have, because of the initialization, they would have the upper hand. They would have a policy that's slightly better, or for some reason they would learn better. And because of that, when you have this tug of war, they would win out, so the weights are going to be moved towards the policy that represents that particular race. And as soon as the policy is moved, they're going to get better data. So the next time when you try to enact this game, the next update that you do, the signal will be even stronger, right? So that they will dominate the other task, because their signal would grow with how much better they get, and they get better at every step because they're dominating at the previous step. So you have this snowball effect. So they get better, and that's why you first learn playing with just one of the race. And then towards the end, when you've actually learned how to play with you've kind of learned that policy, then the gradient will vanish, and then the other starts learning as well. So this is the high-level intuition. We call this ray interference, and we did a lot of simulations with bandits and all kinds of things, and we show that this is happening. I didn't put it in the slides because, so this is sort of simulations. So you can see, so this is the one loss versus the other, and you see you have this sort of weird shape where you first just minimize one, and then you never go into the middle, so you're not learning them jointly. You either learn one and then you learn the other, or the other way around. The reason this is called the ray interference hypothesis is because for Tom this looked like a ray fish. So I don't know if you guys. So it's like, this, we're creating all of these like nice plots, and we're like, this looks like it reminds us of something. So that's where the name comes. Furthermore, I mean, there's some details here that I don't think it's worth going into. You also get sort of this kind of waterfall effect, so you get these plateaus. There's some reason behind this as well. So it's not just that you sequentialize the learning, but also like at the moment where you're switching between games, you end up having these plateaus that are damaging, because as a experimentalist, when you run the experiments and you see that the loss is not improving, you assume you converge and you stop learning. So the slides that I don't have here is that this happens in supervised learning as well. So this has been all motivated as RL, and it makes sense from the RL perspective, because you have this relationship between the signal strength and the quality of the data you have. It happens in supervised learning as well, and the reason there is it only happens if you have deep networks, and the reason for there is because the depth itself creates some kind of non-stationarity, and it's kind of a bit more complicated, and it doesn't really have exactly the same shape. But this is sort of like a pathological behavior that you'd get from neural networks. And now if we go back and sort of what is continual learning, this is sort of the slide. This is for a continual learning talk, so I just stole the slide and tried to make it fit here. So the continual learning problem is this sort of inability to do proper credit assignment, right? So you have this tug-of-war dynamics to do learning, and if this doesn't work out the right way, it breaks things down. And then this has some implication. This requires the data to be IID. So this tug-of-war dynamics involves sort of the IID assumption. That's where the IID assumption comes in. This also kind of hints to the fact that there's no explicit knowledge composition. So the way you learn things is by contrasting to each other. There's no, I'm going to build on what I know and refine it in some way. It's always like through this tension that needs to exist. And this leads to catastrophic forgetting. This leads to slow learning. So in the work, I was introducing this, and I can give the link later on if anyone is interested. I was trying to argue, or we were trying to argue, there's more authors on that paper, that the reason why deep learning is super inefficient is exactly because of these kind of things. So the key that I'm trying to say here is that even though you show all the data at the same time to the system still learns things sequentially. It doesn't learn them at once. And because of that, it's quite wasteful, because while it's learning one thing, you're computing updates on other things that are not being learned. So you're just wasting compute, you're just doing forwards and backwards for no good reason. It turns out that if you don't do those forwards and backwards, it breaks even worse. So there is some hidden reason why you have to do it, but it's not the reason you would like. You're not actually learning those things. You just need to do them so that you're like minimizing the right thing. And the reason this is interesting for the RL world is because in RL you cannot ensure that observations are IID, right? And if we go back to maybe one of the first successes of deep RL, which is sort of the Atari game, Vladny and others, one of the main improvements there was the replay buffer. And the replay buffer, what it was doing is trying to make things more IID locally. Because without it, the network cannot learn. It just doesn't work. Neural networks don't learn well in a purely online setting. There are ways to get something out of them, but they struggle. The issue is, even if you have a replay buffer, you're just locally making things IID. On a global scale, things are still non-IID, right? The data still changes as your policy improves. And this is, this is why, this is sort of, you would not have this problem if you do tabular RL. If you had tabular RL, you would not have this kind of interference. You would not have to deal with this catastrophic forgetting. You would not have to deal with this continual learning problem. But if you do deep RL, you have to deal with it. And if you look at, if you look at Alberta's plan, or whatever they call it, Rich Sutton's latest obsession, right? He's saying that continual learning is one of the central things that you need to solve in order to continue with the RL. And the issue is that it just comes up over and over again. At some point, it comes up, and this is a pathology. So this is sort of my claim, and I think Rich Sutton would disagree with me, but my claim is this is a pathology of the neural network, not of the RL framework. It's a pathology of the optimizer, and you don't even need to solve it in RL. You just need to solve it for a neural network learning on some stream of data that's not stationary. And then once you solve it, you can go back in RL and use it. I think Rich would argue that continual learning is fundamentally an RL problem, and you have to solve it in RL, and it doesn't make sense outside of RL except for toy kind of things.
So may I
yeah, sure.
So if I get it right, the message is we should, in order to solve this, we need to derive another optimization scheme, not one which is basically an unestimated, unbiased estimator of the
yeah.
Right?
Maybe for the online audience, if you could repeat the question.
Yeah, right. So the question is how, the message here would be that we basically need a different optimizer, not a gradient-based optimizer that needs to make this IID assumption. Maybe. The issue is every time people have played with neural networks and moved away from gradient descent, nothing good came out of it. So, I mean, there might be some optimization scheme out there that would solve this problem and make things fine that doesn't use gradients and be sort of very different. I would not know where to start. I think there's a lot of patching and stuff you can do on top of gradient descent to make this better without really not using gradient descent. So, like the replay buffer, it's sort of like a first step, but you can kind of improve from that onwards. And this is sort of like grew into a whole sub-community, continual learning, and you have like lots of methods. They all have issues. None of them really work, but there's like lots of ideas in the air of how to approach this, I think. But I guess sort of the main idea that I wanted to say, maybe this is less interesting, is that this is a deep learning specific problem that somehow it becomes super important because in RL it can't be avoided. Like we knew about this problem from the 80s, sort of in a supervised setting kind of way for neural networks. It's just why would you train a neural network without having the data ID? And in supervised learning, you get some data, you have to train on the data, you test on the data. So, you know, the ID, enforcing the learning process is the data in an ID fashion was trivial, and it was sort of obvious, and it was never thought of something that like needs to be fixed for any particular reason. I think it became a lot more of a, oh, we have to deal with this once we've started interacting a lot more with the RL world, because in RL world, there's no way around it. You don't have the data. You have to interact with the environment to get the data, and therefore the data will always be sort of I mean, you have offline RL, but there's other issues there and so forth. There's no clean solution. There's no proper answer. Obviously, it's not just RL, you know, there are other places. I mean, there's online learning as a community existed for a long time, and, you know, they have their own kind of issues and all this sequential stuff. But I would say for the more mainstream deep learning folks, I think the interaction with the RL kind of brought to the forefront this particular problem. And I just wanted to give it as an example of like a deep learning specific thing that came by through RL. It affects RL quite a bit. Even now, when you do these systems. Yeah, so I think this slide doesn't say anything new. You know, it's kind of repeating the message. And this is, again, it's more on the continual learning side. So there are other definitions of continual learning, maybe to put it out there. This is sort of an optimization perspective on continual learning that I've been pushing. If you like look, you know, reviews or surveys on continual learning, people will introduce it in different ways, and they would argue that the source is somewhere different and has nothing to do with this. But this is one way to think about it. And I think thinking of it in terms of this credit assignment, and again, like maybe the other thing I should warn, because you guys do a lot of RL. So credit assignment means something in RL. Here I mean something different. So here, when I say credit assignment, I'm basically saying, if I have some error, which weights should I change to fix that error? So it's credit assignment within the network. It's not over the episode or anything like that. You know, it's not sort of nothing to do with TDR and all of those things. But I think that's sort of like a big problem, and then gradient descent is part of it. It goes away a little bit with model size. So these were experiments where we're like, oh, we have all of this interference. And then we started saying, well, like the big thing now is to make the models bigger. And what happens if you make the model bigger? And then you have less interference, and then you have less of this issue. So, you know, maybe like one answer is, oh, just make the model as big as you can. I don't think it works that way. I think there's some, you know, limited bit that you can gain by making the model bigger. But fundamentally, you need the interference. I mean, the reason why you generalize is because you have the interference. If you imagine what would happen if each data point would have its own weights and there would be no interference in the gradients, well, that you're back to the tabular case. Basically, you don't generalize, right? That's exactly like having a table where for each example you say, what is the label? And that's it, you know. And that system does not suffer from catastrophic forgetting, does not have any kind of interference, will not suffer from loss of plasticity or any other of the issues that I'm presenting. That system will also not be very useful. That's where we maybe started many years ago, and it didn't go very far. That's one thing. The other thing where I don't have an answer for it, and you guys might correct me if things have changed, but as far as I know, the intuition in RL is that if you make the model better, you get worse results. So compared to deep learning, where you just make things as big as you can and there's no limit, there is an issue in RL where if you make the model bigger, at some point, actually, it works against you. And I don't know of a paper that studies this properly. My guess is that it has something to do with the implicit regularization of size. So I had some slides at the end for this, but maybe now is the right time to talk about it. I think that, or maybe, I don't know, maybe you're aware or not, but there's a lot of theory now in deep learning that says that if I make the model larger, the size of the model itself acts as a regularizer and forces the solutions that you learn to have small norm. And that's why you generalize better. And there's ways of like showing that. So there's I guess maybe you've heard of the word double descent and Belkin's work. That's what it is about. It kind of tries to make this argument that the size of the model acts as a regularizer. It's called an implicit regularizer. You don't have to do anything, just make the model bigger. And I think the reason why that is hurting in RL is because if the size acts as a regularizer, that means that the functions you would learn with larger models are going to be smooth or smoother than the functions with the smaller model. And I think in RL, a lot of times the objective, the value function that you're trying to mimic, it's actually very non-smooth. Many times you have very nearby states that leads to very different returns because there's one crucial action there that changes the whole thing. And even though these trajectories look the same except one action taken somewhere that might have not even changed the observation too much, the value, it's completely different. So there is this tension of, like, do we want these functions to be smooth or not? So I guess in the typical machine learning literature and so forth, the intuition is like Occam's razor, the smoother, the smaller norm, the better. I'm not as convinced, and hopefully I'll get to talk about that in the RL setting. This is evidence that this idea of interference is happening everywhere. So I said maybe this is the reason why learning is so inefficient. So this is, I'm not going to go into details, but for example, in one of the papers, the first one, they're looking at a number of forgetting events. So they're looking at an example. It's how often you get it right, and then you forget, you get it wrong, and then you learn it again, and you forget it again. And you have, up to 30 forgetting events in learning CFAR, which is super small. And if you go to bigger data sets, you have a lot of these forgetting events. So it's not necessarily just about multitask learning. Even within a single data set on something super vanilla like ImageNet, you go through this process where you learn how to predict certain classes, then you forget it, then you learn it, then you forget it. And that's potentially where some of this inefficiency in learning comes into play, because you don't have this sort of process, or when I've learned something, that's it. I can move on, and I'm just going to focus on whatever is left. That doesn't work with deep learning, and doesn't work with neural networks.
Do you think that this inefficiency comes from because we have so many modalities, information just crammed, aggregated in one number? Disentangle this and try to enrich basically the optimization process of the target?
So the question is whether this inefficiency is coming from the fact that we have, I guess, a rich distribution with many modes and things like that, and then they're kind of. I don't think so. So there is maybe the richness of the data and the fact that the representation itself or the data is presented in a sort of very entangled way, which I guess was part of your question, so it's not disentangled, creates the problem. I guess maybe the one thing that I would try, I think that's fair. What I would try to say, because that's how I thought of the question when you first asked it, is that we shouldn't think of this interference as necessarily being a bad thing. I mean, maybe that's part of the message. So I'm saying that because personally, that's how I thought about it. And I spent time trying to come up with optimizers that would reduce or remove the interference together. And I think that if you reduce the interference, actually, you end up with solutions that are not good. And the reason for it is that there are many reasons. Like even in this forgetting event, so sometimes you might say, I'm classifying a picture of the car as a car, and I don't want to forget that. But if you look into it, it turns out that the reason you're doing that is because you see that the background is blue, and you said anything that has a blue background is a car. So you do want to forget that. You want to learn a different way of classifying the data that relies on different features. And at that point in time, you don't have those better features that would give you the better, more descriptive thing. So I think that the richer the data, the more diverse data, and the smaller the model, the more interference you get. But I also think there's something quite positive about this interference that you don't just want to remove. You'd want to deal with it differently because the way we're dealing with it is very inefficient, right? Like deep learning is extremely inefficient. And then if you plug this in an RL system, you're multiplying this inefficiency quite a bit. RL is inefficient, deep learning is inefficient. You combine them, like everything is inefficient. So it's not what you want. So you'd want to at least one of the components to be sort of more reactive and learn faster. But it's not clear how to do that and have generalization. And I don't need to finish my slide. So let me know when I'm running out of time. But on the generalization point, maybe another thing that I would suggest, another thing that I've mentioned that I've seen sort of RL folks sometimes fall into this pitfall where they don't put a lot of value on the ability of the function approximator to generalize. But just to emphasize, like the only reason we have success is like AlphaGo, alpha star, all of those things, is because the function approximator is generalized. That is the secret sauce, right? So in AlphaGo, I mean, they keep saying that thing. I don't even know who thought it's meaningful, but it keeps, you have as many board configurations as more atoms in the universe or something like that, 2 to the power whatever. The point is that there's a lot of structure in that space, and that's sort of what the neural network is doing, right? So the way AlphaGo works is you have this value net that you use, in MCTS, at the end you use a value function to, because you're not going to be able to do the tree all the way down because it's too big. And the only reason it works is that because that value function actually generalizes, and you give it some configurations of your board, and it says, oh, this is the value, and the value is relatively okay, and then you can use that. And the reason it generalizes is because there is a neural network in there that has all of these properties. So, I'm saying this because, I don't know. There's a few slides in the future, I guess, when you're talking about the plasticity. There's all of this. Anyway, I'll talk about it later. So there's all of these things about feature collapse and so forth. And Sergey Levin has this paper proposing a regularizer that was trying to get rid of feature collapse. But if you looked in the form of the regularizer, basically would force the neural network to behave as a tabular model. And it's counterintuitive. That's exactly what you don't want. I mean, sure, that eliminates this problem that is annoying, which is the feature collapse. But if it would really behave as a tabular model, you'd be in big trouble. Like this system will not be able to solve any of the Atari games. So there is like a middle ground that you want, and it's a bit unclear how to get there. And sort of just on top of that, I wanted to mention Maciej's paper. So this kind of interference and forgetting, it's kind of important. So we found that particularly because you have this interplay between the policy and how it works, and sort of how learning works, you see that when you fine-tune RL models, this becomes a big problem. Fine-tuning RL is not as straightforward as fine-tuning supervised models. You can see this empirically. You try to fine-tune them, it doesn't work as well. Supervised learning, the best transfer setting is just fine-tune. In RL, is not the case. There are multiple issues. This is one particular. There is another issue where you have sort of this dip in performance as soon as you start fine-tuning, and usually that is because of the bootstrapping. So what happens is now, instead of your bootstrap estimator is super biased, so you're moving in the ascend direction instead of descend direction almost always, and that breaks things. But there is also this, so the way we've explained this, so this is a complicated graph, and you can look at the paper afterwards if you're really interested in it. But at a high level, the story here is, if you imagine your state space split into 2 sets, states that are close to where you start and states that are far, when you have the transfer setting, when you go to the new task, your policy is not optimal already. It's either imperfect on the new task, or you basically just don't know how to behave in the close by states. What happens as soon as you start learning how to behave there, just because the way the data you see is the data collected by the policy, the data is just around the states, you don't get to see sort of the far states because you never reach them, your policy is not good enough. This almost becomes like a continual learning problem where you're basically stuck in the close states, you spend a lot of time learning on that, and when you're learning on that, you forget how to behave in the far states. And then when you get to that thing, you end up it ends up not working. So these are some kind of examples. So maybe the one above. So we have this robotic arm task, and what we do is we concatenate different things that you have to do. So basically, say you have an arm that learned how to pick that ball and place it somewhere on the table, and now you have another task that says, well, open the drawer and then pick the ball and put it inside the drawer. But you already know how to pick a ball and put it in at this particular position. You just need to learn how to open the drawer now. It turns out that as soon as you start learning on this sort of new task, which is open the drawer and put the ball there, you forget how to pick up the ball. So if you measure your performance on just picking up the ball, is as soon as you're trying to learn how to open the drawer, you forget how to pick up the ball, and you don't see any transfer. So overall, I don't know which of these graphs is the right one to point to, but overall, what turns out, I mean, the graph I mentioned, so the one on the top is the setting where I've mentioned, where you see, so the blue is the performance on the first task, which is just picking the ball. The yellow is the performance on the second one. And then the idea is that as you're learning the second one, the yellow one, your performance on the blue one for the dotted line, which is just vanilla fine-tuning, it just drops completely. And the point is, like, if you look at overall, like, how long does it take to learn to open the drawer and put the ball in, it takes you as long as if you learn from scratch. Like, the fact that you've learned before that how to pick a ball is not useful at all. But if you start adding sort of like continual learning techniques to mitigate this kind of forgetting, you see some boost. You don't see the boost that you'd like. You don't see sort of exactly what you'd expect. You know, if you measure how long it takes you to learn just open the drawer, and you don't see that composition perfectly. Like, you just see a bit of boost because you've added a bit of continual learning to it, but that's about it. How am I staying with the time? Okay, let's see. So this was a lot about forgetting. So there's all of this interference, and this interference in RL is very problematic because the data you see depends on the policy. So whenever you have interference and you forget something, then you don't get to visit it. So I think maybe as a message here of the RL-specific side of this catastrophic forgetting problem is, if this would be a supervised task, if you forget something, it's not a problem because you just see the data. You have the data. Say you're doing multitask or whatnot. You have the data. You have the right labels. You can kind of recover it. In RL, the problem is if you forget some behavior, like, for example, picking up the ball, then you don't have the data anymore. It's not just a fitting problem, right? You need to do the exploration involved in figuring out, like, how to pick a ball and sort of how to see the reward. So the issue in RL, why it's so much worse than it is in supervised, is that the data you see depends on the policy. So this is for the online RL. So for offline RL, it's a different story. I'm not going to get in there yet. But and this makes catastrophic forgetting more important because whatever you forget, it's really hard to recover. Yes?
Is maybe the issue because of we don't have proper abstractions or ways to regularize to learn proper abstractions, and we just memorize features if you want, so in the latent spaces?
This is for the forgetting part. Yeah, so yeah, I would agree with that. I don't know how to do that, but basically the way I used to phrase it, which is differently, it's more deep learning way, is when we do an update, the update touches all the parameters of the model. So when we're doing this first order gradient descent thing, we're independently asking for each parameters. And there's no locality of the updates. If the updates would be more localized, and this would happen when you have abstractions and you have structure in your architecture, you're just learning the right components or the right interaction between the right components. If things would be more localized, then there would be a lot less interference, and then therefore things would work better. I don't know how to create that localization. Yes, there are two questions. The reward function is? The reward is dense. Yeah, the reward is dense. So you can see that in how quickly it learns every task. It's more of a demonstration, but yeah, the reward is not sparse. Yeah. So they have the shaping reward that's cooked in the task. Yes, sorry, the question.
Correct me if I'm wrong. Do you think that there is no way that you could make neural networks and freeze some layers? And like the initial image processing, you freeze basically, you learn stuff, the high level stuff, you freeze it, and then so you mean in RL you don't do that?
We don't. Well, in these experiments we did not freeze anything. I think it's becoming more popular. It's becoming more popular, but also, correct me if I'm wrong, but like a lot of the recent works that I've seen in this direction tend to be in the offline RL anyway, not in the online RL. So I think there's a slight movement towards more and more offline RL. Offline RL where you're doing imitation learning or something like that, you have expert trajectory and you just imitate them. Like I'm thinking of things like decision transformers and all of these things. In decision transformers, it's natural to maybe freeze some part of the decision transformer, pre-train it on something else and so forth. There are some experiments in online RL where we use like a pre-trained vision pipeline, say some ResNet trained on ImageNet or something like that, and you just put a policy on top. These things can help. Pre-training can help. They can hurt as well. It depends on what kind of pre-trained model you have and how well it covers the distribution of the observations that you see. Because if you freeze that side, you can't really correct it if like it doesn't extract the right features for whatever reason. But you're right, it can help. The continual learning problem, it doesn't go away just because some layers are frozen. You're just going to have interference on those layers that are not frozen. But it might be less interference, or it might be easier to deal with. Or if the representation you learn is somehow disentangled enough, kind of going towards the abstraction point of view. I mean, that's another way of thinking of abstraction. You just have a very disentangled representation where you can say, oh, this group of units just represent this object and those group. And then obviously you have less. But deep learning, they learn rich representations, but they're not disentangled. There's a whole field of like learning, you know, beta VAE and all of this stuff to get disentangled representations. But even with those, they're not really disentangled. I think there's also like a more of a philosophical question here, which is depending on the data that you're using and how you're using it, which is there is not one way of explaining the data. And you know, like if you push sort of this disentanglement too much and you have the wrong decomposition, it's really hard to go back from that. But that's sort of a different, I mean, basically what I'm trying to say is that I feel like what you need is not just a disentangled representation, you need a set of them, sort of like a set of hypotheses of how you could interpret the data, and then try to figure out which one is the right one for the task you're using. And we don't have that. I don't know of any method that does that. But I think that's where we need to go. But yeah, I mean, there are, I guess, modularity, abstraction, stuff like that are part of what people are considering for continual learning and are potential solutions. I don't know of anything that actually, I mean, I know things that work somewhat, but I don't know anything that really, really works throughout. But it is a good direction. It is a valid direction of approaching this problem. Okay, so there is the interference that says, when I learn something new, it breaks what I don't have. Nowadays in RL, in the deep RL world, there's been a lot of talk about plasticity. Rich Sutton had a paper at Nature recently on plasticity that I think there are better papers on plasticity, but I mean, I understand, well, I agree that his paper should have been the Nature one because he's the first one who pushed this, but I think his paper like misses the point of what plasticity is. But what's going on with the plasticity? So this is, okay, so this is the stuff I was talking about with the implicit regularization. So this plot, I don't know if you've seen it before, this is Belkin's paper of double descent, right? So he had this paper, it was a big thing in deep learning at some point where he was saying, if you do ML, typically what you learn is like if you increase the capacity of the model, you know, if you have an parameterized model, you increase the capacity, the training becomes lower, the test becomes lower. If you increase it too much, you're over parameterized, you start to overfit. Unless you regularize, unless you explicitly regularize the model. If you have a model that's too big, it's too flexible, it starts fitting the noise of the data, you start overfitting. And you have, I don't have a pointer, but the black curve, you know, the first U-shaped thing, that's what you typically expect. So you'd expect training error goes down, test error at some point starts going up because you're overfitting. And what Belkin says is, well, if I keep growing the model, at some point the test error starts going down again. And actually it goes down way lower than it was before. And this is what deep learning does nowadays, right? So when we're talking about the sort of LLMs of billions and billions of parameters, the hope is that we're in that second part of the graph. And then we keep growing it because every time you grow it, it even goes down. It keeps going lower. And this was an empirical observation. It turns out that it's not just neural networks. It's true for linear models. It's true for all kinds of models. All models do this. And the reason for this, oh, do I have the right plot? Let me see if I have the right plot. No, I don't have the right plot. The reason for this is this sort of this implicit regularization. And then just sort of I try to explain it on this plot to see if it makes sense. So what happens is when you are before that peak of the test error, what happens is you have one global solution that is optimal. And as you grow the model, you start fitting the noise, and it's going to be worse than that global solution. Once you go over that, you're so over-parameterized that you're not going to have a single global solution. You're going to have exponentially many of them, right? So the model is so big that there's many, many, many solutions that are giving you the same sort of global behavior. That's kind of the argument. So if that happens, then, and you think about how gradient descent works, then what's going to happen is that you're going to converge to the solution, to the local minima that's closest to you. And that's sort of what gradient descent does. So if you grow the model and you blow up the number of global minimas and local minimas exponentially, then the likelihood of you getting local minimas and global minimas closer to initialization grows quite fast. So what's going to happen is you're going to converge to one of these local minima or global minima that's closer to you. Another way, so I was talking about smallest norm. Another way that this is phrased is that you're exploiting the number of local minimas, and then therefore you're going to have local minimas that are closer to you. But because they're closer to you and you start close to 0, because you just initialize the model, it means that those local minimas will have small norm. And because they have small norm, they should generalize well, because Occam's razor, small norm is good. I mean, that's a standard. So anyway, there's more nuance, and there's math, and there's all of the things within Belkin's paper. It's actually quite a nice paper. I really like Belkin's work. The whole point is, the bigger you make the model, you'll notice that the solutions that you'll find, the weights will have smaller magnitude, and you have the sort of generalization effect. And I think implicitly you'll have a smoothness effect as well of the function, and sort of the problem that I was saying before. But what that means is that the solutions you converge to depend on where you start. And the reason you generalize is because you start close to 0, so you generalize because they're small norm. But if you're in a continual learning, a fine-tuning kind of stage, that you don't have that option, right? So when you start learning the second task, you start wherever the first task stopped. And that could be very far away from 0. Therefore, the solution that you'll have might not generalize that well. You might not have this small norm. You might have this property. And then this is our work in supervised learning that are kind of showing that. So they're doing this kind of fine-tuning scheme, and they're saying that, like, oh, so the pathological example that people talk to, this works? No. I don't know what I did. The pathological thing that people talk about is this Ryan Adams and Jordan Ash paper, where they say you train on half of CFAR, and then you fine-tune on the entire CFAR, and you don't get the same generalization that if you just fine-tune on the whole CFAR from the beginning. So the fact that you've pre-trained on half of the data set, even though it was from the same distribution, harms you to a point that you cannot recover that generalization anymore. This is a pathology of the learning. And then it also comes to initialization. So you have this extreme memorization where it says, if you play a little bit of the initialization, I mean, it's more than a little bit, so you scale some weights by like an order of magnitude and things like that, you get these systems that get 0 training error, but chance test. So the only reason we generalize for neural networks was the initialization. Like, if we change the initialization, even though we haven't broken learning, you see optimization. So you see the training error goes to 0, and you don't see anything weird with the training error. You see sort of this chance behavior. So initialization matter. And this is sort of where the loss of plasticity, I'm going to skip this because I'm kind of, I'm not going to finish the slide anyway. But this is where this loss of plasticity comes into play. So this is sort of the work with Rich Sutton, so the paper on top, kind of popularized the topic. So the idea here is in RL, when you learn, you can think of it as a sequence of tasks. So like take Montezuma, like each room, it can be a different task. You have different observations, different things, right? So there are these sudden changes in the RL task depending on where in the trajectory you are. And this is like learning a sequence of tasks. And when you start learning on the second room on Montezuma, you don't control the initialization. You might already be in a place where you can't learn that well. And people notice this empirically. They notice that if you reset the parameters of the model regularly, you suddenly see boosts in performance. So there was something where the model would not let you keep learning, so you have to reset the models. And there's been a big fuss of where this is coming from. The original Rich Sutton work, they say it comes from the activation function. So they talk a lot about dead units. So they say, well, if you have this ReLU that becomes 0, then it's like you lost capacity, so you can't learn. This connects to Sergey Levin's paper as well that talks about the we try to look at some of these things. So with Claire, we had this paper. We were looking at all of these things. It's kind of weird. So basically, all I can say is there are a bunch of things. None of them are causally determining the loss of plasticity. So I take the dead units. So we have here in one of this plot, right? You have a CNN and MLP. And you can see that some models, they have more dead units and they're performing better. And some models have more dead units and performing worse. So it's not causally, it correlates most of the time, but it's not a causal thing. Like you can definitely get a model with more dead units to perform better than one with less dead units. Actually, the dead units thing, there exists paper in supervised learning that talk of it as a good thing. So the idea is that dead units make you robust to noise and make you generalize better and give you better performance. So there's a lot of nuance. So I think in RL you have this opposite view where every time people talk about loss of capacity, you know, like rank collapse of the features or anything like, there's a bunch of papers in this field, every time it's seen as a negative thing, right? There are papers that just say, regularize that, make it such that your neural network never loses any capacity. All the units are used all the time, assuming that that's a good thing. And in deep learning, you see papers that say the opposite thing. You regularize the model to lose capacity so that it's robust to noise, so it's robust to adversarial examples, so it generalizes better, it correlates with out-of-distribution things and so forth. So there is a tension which basically says that neither of them is right, right? Like because in the end, they're using the same architecture and they're using the same thing. But anyway, so there you have this loss of plasticity. It's not really, so there's a lot of hypotheses where it's coming from. There's a bunch of solutions. So there's a continual backprop, which is the original paper. There's redo, plasticity injection, all of these. They're just sort of interventions. And they all basically just show that the phenomenon is happening. It's a real thing in Atari, at least, and in a bunch of other RL environments. And if you intervene, like you get a boost, none of them necessarily say that the way they're doing is optimal. Or if they say they're wrong. So, and how am I? Oh, 10 minutes. So I'm just going to, yeah, I'll see. Maybe I'm going to skip a few slides too, because I think there's some other things towards the end that are somewhat interesting. In the latest paper we had on this topic, I think, again, this loss of plasticity is really like a deep learning specific phenomenon that is affecting RL more than anything else. But the issue really is one of signal propagation. So the problem there is how well, you know, when you're computing this gradient, how well is information flowing from the top to the bottom of the network? And this is sort of something that people in deep learning studied, right? When we had all of those papers about how to initialize weights and stuff like that, it was always about signal propagation, right? You wanted to say that, well, my function, you know, needs to be sensitive to any of my observations, right, in order to be able to learn from them, because if you cannot see observations, then it's not going to be able to learn from it. And you want the magnitude of the gradients as it goes through the layers, or the magnitude of the signal as it goes forward through the network, you know, not to vanish, not to explode, to kind of stay within the same range. And it seems that like loss of plasticity basically has two sides. So it has sort of this distributional shift of pre-activations. So one thing that maybe is not even clear to a lot of people working with deep networks, but the activation function that we use, they make an assumption on the distribution of the pre-activation values. So ReLU, for example, makes the assumption that the pre-activations are Gaussianly distributed. If they're not Gaussianly distributed, ReLU is not going to work well. And what happens is when you learn, so you know, you kind of match the distribution at initialization with the activation function that you have. But as you learn, obviously, this distribution is going to change. And sometimes it's going to change so much that the activation is not going to do what you want. So for example, for ReLU, there are two pathologies that can happen. One is all your pre-activations become negative, and then the ReLU is 0 all the time. It's that unit, and that's sort of what Rich Sutton is talking about. You have another pathology where the pre-activations are always positive. So then the activation doesn't introduce any nonlinearity in the system. So again, you're losing capacity. Like the model is actually not functioning. So they call this, I think, dormant or zombie neurons or whatever. They have a bunch of names for them. But you have these neurons that are actually always linear. And then if they're linear, they're not, like the network needs to maximally be nonlinear. You know, half of the time be 0, half of the time be linear. So that it actually introduces like ability, expressivity in the system. And this comes from this distributional shift that you can control with normalization layers and stuff. But of course, normalization, it just fixes the distribution to the first or second order degree, right? You know, like if you have like skewness that's kind of weird, like, you know, dividing by the variance is not going to help you. The other thing is the weight magnitude. And this is something I've never appreciated as much. But if you think of you can think of your learning rate and you can think of the effective learning rate. So the issue is, even if you normalize the signal, and the signal always has a good sort of magnitude throughout the model, if your weights blow up and you make an update that has small norm, that's not going to change the behavior of your function. And if you make an update that has high norm, you know, that's going to make a difference. So basically the weight, the magnitude of the weight acts almost like a control on the learning rate. It creates sort of this implicit learning rate that sort of depends on the weight magnitude. And you want to control that as well. And yeah, yeah. basically, so it seems like at least we know these two play a role in here. These are deep learning, traditional deep learning problems, and they create all of these plasticity issues that really harm RL, and we've seen a lot of times that just playing with it gives a lot of boost. If I'm correct, I only have 7 minutes, so I'm going to jump a few slides. I also want to see if people have questions. There is I wanted to talk about sort of spectral normalization. These are sort of optimizations. Optimization matters in RL. People don't study it. It turns out that if you play with optimization, things change a lot. This kind of loss of plasticity in the sense of like losing, like having your rank of your units to decrease also affects things like PPO. It turns out that PPO basically just breaks down if that happens, just because of how PPO works. So we did studies like this. But what I wanted to jump to, so I could come back to this if people are, if we actually don't have what to talk at the end. I wanted to talk a little bit about the reverse. So we talked, I mean, we haven't talked about all of this, but there's a lot of pathologies coming from the deep network that's affecting RL, a lot more than affecting deep learning. So catastrophic forgetting, plasticity loss, this kind of implicit regularization effects. What's interesting about them is that they're actually affecting the RL problem way more than they affect the supervised learning problem. Therefore, there's not that much focus on them purely. I mean, for catastrophic forgetting there is, but there's not as much focus on the supervised side because for them it's not as important. It doesn't affect the usual stream of how we do things. But for RL, they're kind of very important. I think that creates sort of exciting problem. The reverse is true as well. And again, for the folks here who've done a lot more RL than me, maybe this is obvious, but we had this paper, we were trying, at some point there was this theme of trying to say, I want to learn the RL system, but I also have some expert, and I want to distill from that expert while I'm learning. So I want to speed up learning. So this kind of this kind of distillation strategies were quite popular in supervised learning. They help a lot to speed things up, and we're like, okay, can we distill from a suboptimal expert, or can we combine things? And then it works. There are papers on this, and there's some kind of curriculum that you can build and all this kind of stuff. But like the funny thing that comes out when you start playing with this, you realize that RL is interesting as a deep learning person. When you do these things, you have that mindset that you typically have when you work with neural networks, is that you have an objective. You're working, basically you're doing optimization. You have an objective, you're adding terms to that objective, and this forms some gradient vector field, and the optimization works in that gradient vector field. The issue is RL updates are not gradients. In many cases, there's no objective that you can take a derivative of, and you get sort of the RL objective. And this is something we don't always think about it. And why is that important? Well, it's important because if you work with gradients, adding to gradients, you get a gradient, right? It's always like that. They decompose very nicely, and you don't have to think about it. If you don't work with gradients, adding to things, you don't get a vector out of it. So therefore, there's no reason for it to converge. And you can easily come up with problems where you show that, well, because I've added this regularizer, it makes a lot of sense. Now, this will end up in a cycle, or it end up in some kind of chaotic behavior. The nice thing about like gradient vector fields is they have these point attractors. You let it run, it goes to the point, that's your convergence point. But now in RL, like when you add these terms and you don't think about them, if you just think of them as an optimization problem, you say, oh, I'm going to add this regularizer, that regularizer, I'm going to add this thing, and I'm going to sum it with that, you might end up with something that just doesn't converges. It just diverges from the beginning. And I think this is kind of interesting. Mathematically, it's definitely true. Empirically, it's not as big problem as we think, because we've been doing this a lot. We've been adding terms without thinking about it, and it kind of worked. But in this paper, we kind of showed when it doesn't work, and we took most of these are proposed papers, I think, and we looked at them to see how many of them are gradient vector fields, and not a lot of them are. So the one with the stars, I think some of them you basically need to do some correction to actually make it into a gradient vector field. If you really want to, the method works without it. But the idea is that, like on policy distillation, which was a paper that people like, it's just there's no loss, right? These updates form no loss, and we don't have any reason to know that converge. So, so I think the reverse is also true. Like you shouldn't think of RL as just being another optimization problem where we just have a loss. We actually don't have a loss. We have some updates. There's some theory of why those updates converge. That theory makes some assumptions. If those assumptions go away, it doesn't have to converge, right? It has to be some kind of contraction. The updates have to build some kind of contraction. The other thing is this smoothness thing. And I think people talked about control. So we did this task here. We thought like, oh, we actually did a bunch of tasks that we thought it's just going to work out, and it didn't work out. And you realize afterwards. So this task is kind of like a silly task. You have this rocket, and you want it to give some initial force, and it needs to land somewhere. And you have this planetary system, and it just needs to like figure out the, this is Newtonian physics, but this can be chaotic, depending on how you put the planets. Like the behavior is quite messy. And the issue is when you try to learn this with model free, it doesn't work because the value function that you need to learn looks very nasty, right? If I make this system chaotic, like any epsilon change in the initial conditions changes the value completely. And the neural network just cannot represent that. So if you need to control something that's chaotic, it's quite problematic to control that with a function approximator that's a neural network that assumes that the function is smooth. I was trying to make a toy example here, but I'm not going to. I think this is kind of interesting. Another place we're trying to do, I think this is Kepler did this. So we're trying to do this reverse thing where you say, okay, you have some system, like some planetary systems, and you observe, so it's like n objects and n bodies, and you observe n minus 1, or at least you assume you observe n minus 1. So you observe n minus 1 planets, you assume there exists another one because something looks fishy, and you want to, from the observations that you have, you want to derive what's the position and the mass of the object you're not seeing. And if you try to do this with gradient descent, it just kind of breaks down again, depending on how you set up the system. Because it can be chaotic enough that you cannot actually derive the initial conditions to get exact those movements, right? Things just explode. Yeah, I don't know if you guys agree with me or not. But anyway, I don't see this discussed enough in RL. But I think there is an issue where you can have these systems that are very nonlinear, very chaotic. And then it becomes a real problem of, is the neural network good at approximating these kind of functions? And in general, not, at least not with a bit of help. They like smooth things. And I feel like, again, this is something people don't consider, right? They say, well, I'm just, pick my PPO thing, take a ResNet, take whatnot, and do not take into account that, size will regularize that thing to be smoother. The choices of layer norms are going to make it to be smoother. This will make it to be smoother. And it just cannot represent what you care about, and it's not going to be able to do that, solve that task. And I think, again, this is a space where maybe, at least in this kind of, I don't know how many of these chaotic tasks exist, but in these ones, I think we need to innovate on the deep learning side, because it's not going to work like that. And I'm just going to stop here. Thank you. If you guys have questions, happy to answer. Yes?
Correct me if I'm wrong, but it kind of fits to the last point. The transform architecture, for instance, took for a very long time to really make it work in the setting of an RL setting to learn.
Yeah.
Is it maybe implicitly by just memorization effects of the transformers,
so
that is kind of like creating even more harm of nonlinearity?
With respect of this, I don't know if this is the right term. I call it non-smoothness of the value function. With respect to this non-smoothness property, I think the transformer actually helps. I think this memorization actually allows you to represent things that are sharper and less regular. So there is an issue with the softmax. I think I've mentioned this before. So so basically the issue is you train the softmax with some context length, and it kind of learns what it does. It grows. It basically needs a particular temperature to have, the softmax needs to have a particular temperature in order to be sharp enough on the thing that it needs to pick. And it can do that by growing the weights of the key query and so forth. You can think growing the norm of those weights is like changing the temperature of your softmax. It does this on a training set. So then at test time, if you make the context much longer, in some sense, basically because you've added all of these elements, you're going to have probability mass that is kind of seeping out of the most likely one. And what's going to happen is you can actually make the thing look uniform. So basically it loses all kinds of sharpness. So one kind of pathological thing that we find funny is softmax is meant to simulate a max. It's a soft version of the max operator, right? So it's funny that with a softmax, with the attention layer, you can't really represent a max operation. So if you try to learn an algorithm that is just trying to pick the max of a set, you can show that at test time, if you make that set big enough, the system just cannot pick the max. even though you know it has the right construct, because it just, that's exactly what it does. It compares the distances and picks the max. But because of this shipping of the probability, like it just becomes flat, and then it just doesn't give you the max anymore. It just doesn't know which one is the max. So there are pathologies with the softmax. There are pathologies with the transformer. I would say if you work within domain, within the data distribution, so not increasing the context or whatnot, in general, I think it will be better at dealing with sharp things. The same thing goes for this gated MLP or these multiplicative interactions. They, again, help you to do sharper things. So there's some stuff that help. Yeah.
There was one, because I think
Yeah.
one takeaway is that we can just train an agent one task and deploy on the other task, right? Then because then apparently it will use the first one. So I'm just wondering when you at DeepMind trained the agent for the Atari games, right?
Yeah.
Did you just play it all at the same time?
Right? Yeah. So all of this Agent 57, whatever, they're always trained in multitask learning. If you track the performance on the individual tasks as you're learning, they're not improving at the same rate. There's going to be some games that learn very fast, and then some games that learn at the end. It's going to be almost like a progression. There's almost kind of like a sequentializing of the learning process. But if you're not doing the multitasking, it doesn't work. So like even though you're thinking you're wasting compute by keep playing these games that you've already solved or playing these games where you're not making any progress, if you don't do that, like it just breaks completely. So that's what people do. I mean, there's some things like in CTF, they had this sort of risk-adverse thing where if a task is too hard, you just throw it out. Because what happens is like the hard tasks, if you're not learning on them, you're going to forget them. But the point is there's nothing to forget because anyway, you don't know how to play them. So you can be sort of, you can at least throw away things that where you haven't made a lot of progress. So you can do this kind of filtering online. And they found that sometimes it's useful. So in this kind of settings, they had this setting where you generate tasks automatically, and sometimes these are just ridiculous tasks that can't be solved, right? So generate the task, you look at the return or like the rewards that you see, and if it's just nothing, you just say, well, I'm not going to learn on this, and give me another task until I see something where I have some signal I can learn on. Yes?
What was the correlation between the forget events and the local minima during that time training?
So, sorry, what is the correlation between the forgetting events and the local minima?
Do they occur at the same time, or it doesn't matter?
So like those forgetting events are happening on the way towards the minima, right? So that's a system that's training. So there's no, I mean, it's not like you're jumping from one minima to another. I don't know of any. So the thing is the loss is monotonically decreasing in the supervised case scenario. Like definitely, if you're training a supervised system and you see the loss not monotonically decreasing, something is bad. It's no like funky thing. It's really like something is wrong in your setup. Like the loss has to be monotonically decreasing. I don't know exactly how this balances out. That's a paper I wasn't part of. This was a Mila paper. I don't know how. I don't know if I have an answer for you, but there's not multiple minima. There's one. The only one thing that I would say is that people have noticed that the minima is not a point. That's another big mistake that sort of we typically think of minima as being a point in the parameter space. It's an area that is weirdly shaped, and it matters where in that area you end up because you're going to generalize differently.
These minima, for example, when you're estimating the value function, for example.
Yeah.
Since it changes with the policy, you might end up with some local minima when the policy has changed.
Oh, right. You're thinking in an RL setting. So I don't know of any experiment done with those kind of forgetting events in an RL setting. I would agree. You can imagine that they have this cascade of different functions that or like different objectives that you're minimizing, different losses. And yeah, they will capture only a subset of the state space. So, maybe it's connected to that as well in the forgetting. Yeah, I think.
Because then the forgetting events become essential.
Yeah. Yeah. Yeah.
Do you think that RL can still be just scaled at some point if you have enough environments, enough, if you want the complexity, that we basically then, it smoothens out again and we have this kind of double same way of.
Yeah. I'm not sure. It could be the case. I wonder, and I think there's maybe a question for deep learning as well. It just maybe we're not in the right place to see this effect. I wonder, this is like like the universal approximator kind of thing, where it's like, or like, yeah, basically, if you have infinite scale, probably at some point you don't need anything. You know, there is this proof that if you have a vanilla RNN, like Elmon's RNN from the 90s, and you have infinite size, and you have infinite time, and you know, infinite data, it can approximate anything. You know, it's Turing complete. It can do whatever. It can learn anything, right? So, and then at that point, but people did not stop doing research at that point because they say, okay, we have the solution of AI. It's just this Elmon network. We just can't. Or IXI, sort of Marcus Hutter. It's another, you know, in principle proof of a way of constructing a AGI that is provably the best thing ever, but it's just uncountable and so it could be that maybe that's an answer. There's a question: is there a more efficient thing? And if there is one, wouldn't we want a more efficient one? But I don't know. Definitely scaling helps. I think a lot of the scaling schemes that people are doing now, this is my feeling, maybe I'm wrong, they're a lot more on offline RL than, and the reason for that partially is because of the decision transformers. So there is an obsession that we have to use transformers. Transformers don't work as well in online RL as they work in offline RL. So therefore, everyone is doing offline RL because decision transformer works and it's easy and you have the setup and you just throw more data. So I think there is a bias like that, and a lot of these bigger scale studies tend to be in this kind of offline setting. But it might be working perfectly in online setting as well. It's just a bias in the community, I think.
Thank you very much, Razan.
No worries, thank you.
Good round of applause. There'll be so many more questions, but we have to move on to the next speaker also. But first of all, we also want to make a sort of a group photo together. So we want to use this chance. Maybe Simon, I don't know, how do you imagine it, or how?
Yeah, I guess we should go to the building adjacent to this one, like the main entrance of the tower over there. And there are two things, like sorry, yeah. basically the tall people to the back and kind of not so tall people in the front. And if you have like
To the audience, we're going to be back in a minute.
Okay, so just an update for the online audience. We'll start in about 2 more minutes, continue with our presentation. Okay, so I think we're going to start with the next section. So there's some discussions in the back, but I think we can start without them, and we'll try and make up a little bit for lost time. So our first talk, it was kind of like the teaser, get everyone into it, and now we're going to take a big step back and try and start with the very basics again. So this is a boot camp. We tried to make it available for people of all different levels. So at this point, we're going to start at the very beginnings. For some people, this will be something you know already. One tip I got from my PhD supervisor a long time ago was everyone's happy to hear something they already know. They feel good about themselves. It's good for the ego. So if you're in that camp, it's good for the ego. Otherwise, this is for people who have maybe not done a lot with reinforcement learning up until now. We're going to start from the basics. In the very least, we'll all have the same language that we can have discussions later on. So my part here will be really the very mathematical basics of reinforcement learning, and then Thomas will continue after that on a little bit more details of different methods. Now that, maybe Simon, can you send Marius back in? Because the clicker is not working. Some technical difficulties. But in that time, I can start anyways, because I don't need my slides. So what are we trying to answer in reinforcement learning? And the types of questions we're trying to answer are sequential decision making. Sorry, the clicker doesn't work anymore. Oh yeah, that's thank you. Okay, so what are we trying to answer when we're using reinforcement learning? Obviously, it's not a method for everything. We're trying to answer sequential decision-making problems in dynamic environments. And every aspect of that statement is important when choosing reinforcement learning versus something else. And what are we going to have? We're going to have an agent who makes a series of decisions over time, and each decision potentially affects future outcomes. We need this dynamic aspect, otherwise there's a lot of different methods we can use for optimization. The environment in the background is dynamic, meaning it can change in response to what we just done. And our goal in the problem that we have is to learn a policy, which is to learn a set of actions that maximizes the cumulative rewards over the entire, what's called an episode, or minimize the cost over time. A lot of the famous examples, they're things like chess, like obviously everyone at DeepMind, they were working on Atari games. They were kind of these computer game structures. But what are we trying to work on? And a lot of people, I think, in this room are more kind of practical users of reinforcement learning. We're not trying to solve a computer game where it kind of doesn't matter how many resources we invest. We want the best response in the end. We're kind of working on more real-world practical problems, things like job shop scheduling is something that reinforcement learning has been used for. Energy management systems is a project I'm working on. Routing algorithms, autonomous driving, there's a lot of work on reinforcement learning, obviously robotics, resource management, and here the list kind of goes on. But the success in these kind of use cases has been a lot, I would say, smaller than of those computer games. There's a lot of reasons for that. I find those reasons are actually quite interesting also on a theoretical level. And I think that's something there's a lot of active research going on to where can we find success and at what costs. And what's the basic idea of reinforcement learning? It's a computational approach to learning from interaction. So that's really the basics. Actually, our co-organizer, Marius, he had a new baby. And when you see a new baby, it's actually really interesting to see how babies are learning. They're constantly interacting, they're constantly getting feedback, and that's how they learn. And that's what we're trying to copy in a computational way with reinforcement learning. What is it about? We're going to map situations to actions. So we have a state space, we map that state space to a specific action, and that action should maximize our goal. And our goal is in the form of a numerical reward. And our learning is characterized by trial and error, and it's characterized by a delayed reward. So we don't necessarily have to get the reward immediately. It could be that we get the reward for the action we take now in several steps down the road, or maybe just at the end. The topic of sparse reward is then something very important, but also involved. Okay, so we're starting with a warm-up. The warm-up is the so-called bandit problem. The reason for this is that it's kind of like a simpler problem to that we're focusing on with reinforcement learning, and that it's non-associative. We don't have any states. We have only one possible state, and from that state, and that state remains constant, but we are faced from this state repeatedly with a choice of, in this case, k different actions, and each action has an expected or mean reward when that action is selected. That's called the action value. And this setting kind of gives us a very simple framework where we can learn some of the basics, and then we'll move on to the whole MDP later on. So we have this action value. That gives us this expected reward that we will get if we take this action. And that's given by this action value function, Q of A, and what's just written there is the mathematical formulation of what I just said. That is the function, which is the expectation value of the reward I will get when taking at this time step t the action A. And so you have this value function for all possible actions. In this case, we have k of them, so we would have k of these functions. If you know this value for each action, then our problem is solved. I just look at which action gives you the maximal reward. That's very obvious. And then you have the best action. You have the most reward. The expectation value is that this doesn't have to be, you could have a distribution of rewards that you get. And when taking this expectation value, then you can account for that probabilistic nature. If we don't know this value for each action, then we maybe don't know what to do. And we have an estimate. We can estimate this action value. And the estimated reward is given when the action is selected, is given by this capital Q, and you can just forget that expectation value is accidentally copied down below. So we have this estimated function. We're trying to estimate this little function Q as best as we can, because if we know that, we've solved our problem. Just repeat what I said. So the estimated reward is given by this capital Q function. And when we have this, we have our estimation. We could either choose to exploit, so act in a greedy way, and we choose the action whose estimated value is the best. We can see where that maybe goes wrong, though, because maybe we haven't seen all the actions enough. Maybe our estimation is bad, so maybe our estimated action, which gives the best reward, isn't actually the action that gives the best reward. So to counter this exploitation, we need exploration. That's acting in a non-greedy way. That will enable you to improve your estimation of that action's value. So to reiterate, if we knew the action value, we wouldn't need to ever act in a non-greedy way, because we would know we always choose the best one. But we know we have an estimation. We know our estimation's maybe not always accurate. So in that case, it's important to do the exploration to make sure our estimation is always improving. In general, and this is probably not the case for people involved in more theoretical studies, but in general, it's not really that important how you do this exploitation. You just have to do it. And there are ways to optimize this for particular problems. There's particular ways you should do this. But in general, you just need to make sure you're exploring in some way. OK, so how would we actually do this? Well, maybe we could take our estimate. We could represent in this way. We just take the actual average of all the rewards we've received when taking that particular action. So that's what it would look like. I've taken, in this case, the sum over all the rewards I've gotten when taking this action, and I divide it by the number of times I've done that. And that's basically my average reward. I can keep track of it. I can take my greedy action for the times I want to exploit the system, and that would just be the max, like the argmax of that function, or estimation function. Or in the case I want to explore, I could use the epsilon greedy protocol, which probably all of you have heard. In epsilon amount of times, I'll just take an action randomly. And then I can improve my estimation that way. But if you look at this, if I try and do this online and keep track of this average, I need to keep track of all the rewards I've gotten. That will increase size every time I take a new action. So this is not a very efficient way to store this function in memory. So we need kind of a way to do that, which is more, which is efficient, uses constant memory and constant per time step computation time required. And to do that, you can rewrite the function from before in terms of an update, which means that the new estimation is the old one with some error term, and that error term is determined by the actual reward you got in that time step minus what you would have thought you got on that time step. And you see that this converges when your estimation becomes correct. And that's the general form of an update rule, which is like your new estimate is your old estimate plus some step size minus the error term. And that gives you an online way to keep updating your estimate function. And in that way, if I go back one, we've actually now solved this bandit problem. I just say, OK, keep trying. Every time you'll use the epsilon greedy protocol, you'll improve your estimates. And when you've converged, your estimate function has converged, then you can just act greedily all the time, and you will take the action which gives you the highest mean reward. And this example gave us a couple of concepts that are very useful for reinforcement learning: the concept of an action value, the concept of balancing exploration and exploitation, greedy and epsilon greedy approaches, and incremental implementation, so update rules on our functions. And with this, we can now move on to the actual problem that we're solving with reinforcement learning, and that's a Markov decision process. So this is probably like the most well-known graphic for reinforcement learning. This basically lays out the whole problem. A Markov decision process, it's like the mathematical formulation of a problem that we want to solve with reinforcement learning. It involves feedback, like as in the bandit case, but it also includes the state space. So now we don't just have the same actions from the same state. We have different states requiring different actions. One thing to keep in mind, because also I'm kind of coming to this from a practical point of view, is that this is all the mathematical definition of the problem. And when we're trying to solve problems like this, the mathematical definition gives, especially like theorists, a very firm boundary where you can build up all of the theories. You can look at convergences. You can look at just the mathematical formulation that you can use for your problem. In the real world, it's seldomly the case that your problem fits the mathematical formulation. And then it's really the point of trying to see when do these assumptions fail? How do I work around it? What does that mean for my problem? I don't know if you guys know the joke of the spherical cow. Like, the spherical cow lives in a vacuum, and at some point you're not solving anything anymore. So that's kind of the trade-off you have to think about when solving these problems, especially in a practical point of view. The mathematical formulation allows you the freedom, theoretically, to test a lot of things and make conclusive statements. And in the real world, when those assumptions aren't met, then you need to work and kind of think about the assumptions in the background. What impact does that have on the problem that I'm looking at right now? Just a word of, I don't know, warning. interest for practical problems. But the Markov decision process looks like this. So you have the agent making the decisions. They give the action back to the environment, and the environment tells you what is the next state you're in and what is the reward you got for taking that action. And that process leads to the entire trajectory that you will get. So to reiterate, the action selects the actions to take. Environment will respond to that. It gives the new state that you're in. It will give you the reward that you've got. And the agent and the environment interact in each sequence of discrete time steps. So for the notation, you will have the state t, which is an element of the total state space. You have the action at time step t is an element of the total action space, and the reward at time step t is an element of the reward space. And again, there's also some confusion. Is the reward at t or t plus 1? Just look, there's sometimes a little bit of, it's not always the same if you put the reward of t or t plus 1. But that gives you this whole trajectory. So you start in your initial state, you take your initial action, you get your reward. In this case, it's t plus 1 is for the action at t. And you end up with this whole trajectory. This is a trajectory through your Markov decision process with state, action, reward. And yeah, it's the dynamics of this MDP, so I'll let you try and solve that problem in the background. The dynamics of the MDP are completely defined by the probability of being in some state S with the reward R. Yeah.
We need another problem. Sorry for that. Maybe this one.
I think it has to do with the.
With the remote.
Yeah. Yeah. Apologies for the annoying beeping in the background. A small technical problem. So we have this trajectory from the MDP, and the MDP is completely defined with this probability distribution saying if I'm in this state S and I take action A, what's the probability I end up in a state S prime with a reward R? And if I know this function, I know everything. So this probability distribution defines my Markov decision process. And that's what's actually called, yeah. Yeah, I'll let you work on the computer. That's what's called the Markov property. The entire environment dynamics are governed by this probability distribution, because you notice in the distribution, there's only this one previous state included. So the dynamics of the system only depends on the state that I'm in and not on the history of how I got there. And that's what's, it's kind of a memoryless system is what it's sometimes referred to, and that's what's the Markov property. So that's actually the Markov in Markov decision process. And I think I put a small example here of what that actually means. And this is the example that's on the Wikipedia page, so I can't take credit for it. But you assume you have a container, and it has 2 red balls in it and 1 green ball, so you have 3 balls in total. 2 are red, 1 is green. 1 ball was drawn yesterday, 1 ball was drawn today, and a final ball will be drawn tomorrow. And for this first example, you assume all of the draws are without replacement. So you take them out and they are out. And I know the ball today was red. So that means I have 2 possible situations. Today's was red, so that's fixed. If yesterday's was red, then I'm in outcome 1. Yesterday's was red, today's was red, I only have 2. We didn't replace them. Tomorrow has to be green. The other case is that today was red, yesterday was green. I don't replace them, so tomorrow has to be red. So everything is set. But in this case, the information about what happened yesterday is crucial to know what's going to happen tomorrow. So in this case, this system does not have the Markov property because I need all of this state space information from the previous states in order to understand the system. Because knowing that today's ball is red doesn't give me enough information about the system. Thank you. Let's change the case, though, and assume that we do replace the ball when we take it out. Then, knowing that I have the ball from today, that's all the information I know, or I need to know. That gives me all the information I would need to know to determine what comes next. In that case, there's still the probability of getting red and green is 50-50 after that, because I know that they're both still back in there. And so that system would have the Markov property. So there's actually sometimes in these situations, there's some subtle changes which changes if the system is Markov or not. It's not like a very clear boundary. Sometimes it depends on what's included in the state space definition, if you've defined it correctly. And there I just want to make a note that actually you could say, well, actually I was thinking about this, and if you included all the information about all your previous states in your current state, then everything is Markov. But the point is there's like a problem with bandwidth, and you have to say, actually the rigid definition is that your state space has to remain constant. You can't have a growing state space in time and call it a Markov decision process. Okay, so that was a little bit exclude into what a Markov chain is. Another aspect on the Markov decision process is the expected return. And that's what we're trying to maximize. We're not trying to maximize the reward we get at each step. We're trying to maximize the reward we get at the end of the sequence, or at the end of the trajectory. And what we define is called this expected return. And it's the sum of all the rewards from now with a discount factor. The discount rate gamma tells you how important future rewards are. So it gives you a factor in the future. So the expected return at some time step t, again the t notation t and t plus 1 is not always fixed, is the reward at this time step plus gamma times the reward at the next time step plus et cetera into the future. And that will be useful when we're defining these value functions and these action value functions in the next slides. So the reinforcement learning algorithm, involves estimating the functions that estimate how good it is to take a particular action or how good it is to be in a particular state. So just like we saw in the bandit example, we had that action value which said, how good is it to take this one particular action? And now we have how good is it to be in this particular state and take this action, because we have it state dependent. Of course, how good is defined in terms of this expected reward that I just said. And all of these value functions that we're going to define are defined in terms of specific policies. Because if I say, how good is it to be in the state that I'm in now? It depends, well, what actions am I going to take from this point? Maybe I take really bad actions. Maybe I take really good actions. A value function in that sense is defined based on a specific policy. I have to tell you what I'm going to do in the future in order to be able to evaluate that. A policy is defined by this pi symbol, and it's the probability that an agent will take an action A given the state S. Okay, so let's define our state value function, and that's the expected return that we will get when starting in S and following a policy pi thereafter. That's given by this function v. So this little v is usually the state value function given the particular state S we're in, with the subscript pi, meaning we're following that policy. And that's given by the expectation value of the expected return from this point on. So that's why you have the g of t. They are given that you're in the state S. So that's the notation there. And you can write it out, the expectation value. And that sum there, sorry, the line I think is a little bit misplaced. The sum there is just the definition of the expected return from the previous slide. And then it should be given that you're in the state S. And this value, state value function is defined for every state in your state space. You also have kind of a complementary function, which is the action value function. It's similar. It's just saying when you start in this state, take a particular action A and then follow the policy after that. So that's the difference. You have then a Q is usually the function for the action value function. It's defined in terms of a state and an action, and then following the policy pi in the subscript. And it's just the same definition, the expectation value of the expected return, given that you're in the state S, taking the action A. So those are two kind of fundamental definitions that we need to know. And our whole point of this all is to try and have the best estimate of these functions, and then you can act greedily and you have the best policy. And they can be estimated from experience. So that's what reinforcement learning is doing. It's making estimates of these functions based on experience. If separate averages are kept for each action taken, then these averages will converge to their actual values. But if there are many states, so if you have a lot of states in your state space, it's very unpractical to keep separate averages for each state individually. And that's kind of what we heard in the last talk. It's like, yeah, neural network, it's got all these negative things with it, but it is a function approximator, and it helps you to approximate some of these functions when you have too many states to keep track of them individually. And what is a fundamental property of these value functions? And that's that they satisfy recursive relationships. What's a recursive relationship? It means that a value function for one state can be written in terms of the value function of a different state, and you end up with a bunch of equations that are all intertwined with each other. So let's write that out directly. So you have the value function of the state S. You can write that out in terms of the expectation value of the expected return. You can write that out explicitly in terms of the reward for this step plus the then discounted expected return from the next step. So I'm breaking this down into the one step into the future and then everything after that. And then if you write that out explicitly, assuming we know the probability distribution, which defines our MDP, then you can basically work through all of these lines. It's useful to do it once. We're not going to do it on the blackboard because we're doing this online. It's worthwhile to work through all of these steps. But in the end, you see that the value function of the state S is related to the value function of a state S prime. Because the way you can do it is you can say, well, if I was in this state, I take some action A, and I end up in state S prime, then those two states are related to each other with the reward I got along the way. And that's how you can make this relationship between the value functions of different states. And you end up with an expression which says, if I know the value function of this one and all of this information in between, I know the value function of that state S prime. This can also be visualized because this equation is maybe not the easiest to look at. It can also be visualized in what's called a backup diagram, which people use for reinforcement learning sometimes, where you say, I'm in the state S prime that's on the top. I have different actions I can take from there. And then I end up in different states S prime. And the probability that I will land there is the probability P, and I would get a reward R along the way. And this backup diagram kind of shows you the trajectories you can take through your MDP. For anyone who's done like Monte Carlo tree search and stuff, this is kind of like, you end up with a huge tree of all the possible trajectories you can take. In the simple case, so if you look back, we have all these expectation values that we're like kind of dragging along with us, which is like to be formally correct. If you have the case where the policy only has one action and it's a deterministic environment, you can kind of clean up the equation a little bit. And that's what you get down below, where it's actually a very simple case where the expectation of the state value at a state S is equal to the reward you would get by moving along this policy to the next state S prime with the discounted value. And these equations, these recursive relationships between the different function states is what's called Bellman's equation. So for those who have heard Bellman's equations in the back. So yeah, maybe to reiterate that's what I wrote in the bullet point. The value function of the state you're in right now is the reward you get moving to the next state plus the discounted value of the value function from that next state. And that makes sense. Like, how good is it to be in this state? Well, if I make one action in the future, it's the reward I got along the way plus the reward I will get from that point in the future. You can write the same thing for the state action value or the action value function. So for this Q function, which is dependent on the state and the action you take, you can write down similar equations. So it's a similar exercise to derive this. And it's just saying that this function is also dependent on that function with a different state and a different action. And solving reinforcement learning just means finding a policy that maximizes the reward over the entire episode. And so you can write down these state value functions in terms of the optimal policy. So this is just now a definition. We say that the optimal state value function is the state value function of a policy pi, and I'm taking the maximum, so I'm taking the best policy of those, assuming I know it. So I'm maximizing over the policies. Same thing for the state action value function. And if I were to have this, or if I were to know what is the best policy, then again, I've solved my problem. I just need to act greedily, and I have my optimal policy. These optimal value functions also still satisfy these recursive relationships. So I can write the recursive relationship now just directly in terms of the optimal policy. So there I have this max function comes in because I'm taking the action which maximizes the reward at the end. And I end up with this recursive relationship, and this is telling me how my optimal value functions relate to one another. Again, I can write this function in terms of a backup diagram. And again, just instead of looking at all of the different probabilities or all the different actions which are possible from this state, I'm taking the action which maximizes my expected return, which is the optimal policy. And this optimality equation, if I go back, so up here, what you see is this dependence between this value function at the state S and S prime is actually a set of n equations, for n being the total number of states that are possible in our state space, with n unknowns. And that's actually a system of equations you can just solve. So for those who have worked in mathematics, if you know this probability function, which I said is determining everything about our MDP, then we actually have a set of functions. We could solve it using any of the methods you use to solve a set of nonlinear equations. And you would really solve your problem. You would have then the optimal policy. The point is that this is very impractical and not always possible. And one thing I just forgot to mention is that actually what's cool about this in some sense is that when you have this optimal value function, you just act greedily with it. And even though that seems like acting greedily would just maximize the reward for the next time step, in this function is all of that embedded in this future reward. So even you can act greedily on this function and it's still taking into account this future reward that you will get because that's included in that function itself, just as a note to remember. So yeah, explicitly solving this would be possible, but it's rarely useful. And if it was, we wouldn't be even talking about reinforcement learning anyways. So that's why we're here. Because the solution relies on a couple of different points. One is that the dynamics of the environment are actually known. So you know this probability function P that I wrote down earlier. The second point is that you need to have computational resources sufficient. Maybe you do for a state space of smaller size, but that's not usually the case for bigger state spaces. And three, that the Markov property holds. And like I said, all of this mathematical framework, it's all very nice. But in the real world problems, it's harder then to make sure that all of these things are satisfied. And so what is reinforcement learning? What are we doing with reinforcement learning is we're trying to solve Bellman's equations in a way that approximates it, and in a way that approximates it in the best way possible for our problem. And so what does that mean? There's many ways that we can approximate the solution, and each of them has, like many things in life, each of them has advantages, disadvantages, and they're still being researched, so there's not a lot of conclusive research that says this is the best way. There's a lot of hypes that come up in terms of different algorithms. And it's also depending on what your particular problem is. Like, what of these 3 points don't you satisfy? Because that maybe changes how you want to approximate the solution. And so the last part of what I'm going to talk about is going to be, well, what are different ways we can approximate that? And then in the further lectures that we have, it will be talking about actual particular algorithms and how you implement them. So a couple of different things that you could do to do this approximation is one, do you use a model or is the update model free? So are you trying to learn the model? We assume we don't have a model, so we assume we don't have this probability distribution. Are you trying to learn it? Do you have any information about the model in advance? Are you trying to acquire that knowledge along the way, or do you just not care? You can kind of bypass trying to find out the model and just say, I just want to know what the reward is. And there's different algorithms which then address those. Second point, are you sampling? Are you using expected updates? So do you consider all possible events that can occur based on some sort of distribution model? Or do you just sample once and take a single outcome? Third point you can do is, do you take one step forward in terms of your trajectory, or do you run all the way to the end of the trajectory? So this is called the depth of the update, especially when thinking about this tree form. How many steps are you going to take before you make an update of your functions? Something we heard in the previous lecture a lot is like, are you updating on policy or off policy? So is the policy that you're updating, is it the one that you're using to choose the next action? There's differences in those algorithms. And yeah, this was also the main point of the previous lecture, are you using a function approximator? Because all of this reinforcement learning stuff that we've talked about, it doesn't actually require a neural network. You can do this in a tabular form. You can actually have a table of all your states. You could have, like that's what we'll see, that's what a Q table is. It's just basically saying what is your expected reward for a particular state, and that works really well for small state spaces. And as we also heard, function approximators, they come with a lot of their own problems, but sometimes it's the only way to go. So does our state space require that or not will change how we go about the problem. So there's different categories depending on what types of these approximations you want to do. So there's dynamic programming, when we have our exact model is known, but you're only able to take one-step solutions. There's Monte Carlo solutions where you have the full return, but they're model-free. You also have TD learning, which is only one or n, so usually they're n-step solutions. It's also model-free. Some of the ones that are more popular are SARSA and Q-learning. I'm guessing everyone's heard of Q-learning, and so that's a TD learning, an off-policy TD learning algorithm. And I think this is my last slide, and this is kind of trying to, there's a whole world of RL algorithms out there, and trying to sort them into where they kind of fit to each other. And on the bottom right-hand side, this is kind of the limit of an exhaustive search. So the axes are the depth of the updates that we're going to make on our functions, and the x-axis is the width of the update. If you imagine taking the entire width of the update, the entire depth, and you're really just doing an exhaustive search, you're solving the problem exactly. Of course, you would get the exact solution, but it takes a lot of time. If you go through the width is complete, so you go through every possibility, but just one time step. That's what dynamic programming covers. On the top left, you have temporal difference, where you're just sampling one action, and you're just taking one time step, or sometimes you're taking n time steps, so you can extend that a little bit deeper. And Monte Carlo is you're sampling once and taking all the way to the end of the trajectory. And there's some in between. That's why it's a whole continuous space of algorithms. There's some popular ones, and then there's small changes to those algorithms to kind of make small fixes. So I think that's where I will stop for my talk. The rest of the lectures, you'll hear a lot more in detail about specific algorithms, but I hope my goal for this part of the tutorial is to give a basic kind of reminder for those who already know it on what are we actually trying to do. Sometimes you get so deep into the algorithms, you kind of forget what the goal was at the beginning. To kind of set that stage for people who haven't seen it before, give them the first taste, and then kind of set the stage. I think Thomas will continue with TD learning after this, and then Marius will continue with PPO tomorrow. And I think now we have a coffee break. Do we want to maybe make it, I don't have the time right on me. Do we want to set?
It's great.
Okay, perfect. Then we have a half-hour coffee break. We meet back here for Thomas's lecture, and yeah, thanks for listening.
Test, 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 test. Test, test, test. Geht oder?
Das ist an.
Siehst du, jetzt haben wir
Jetzt, warte mal. Jetzt.
Test, test. Passt.
Passt. Schau. Ja, okay.
All right, guys, let's conclude. Lecture 2. And it's my pleasure to introduce you now to foundations to reinforcement learning. And I think it's also most important to get also the connections to optimal control. So basically this lecture now can be seen to bridge between the talk Marius will give you tomorrow, where he will talk about PPO, and Simon will talk also about model-based reinforcement learning on the bit of optimal control too. So that's basically this lecture should prepare the stage for these two talks. All right. That doesn't seem to work. Oh, sorry. Das ist zurück. Kannst du mir zwei Folien zurück switchen? Ah, zurück. Yes. Even here? So, because the problem is, it's you need somehow to represent the distribution with your neural network, right? Yes. And I mean, these two heads is clear for you, right? Yes. Okay. The second case, because just plugging the observations in there to calculate the variance, because you need to learn the features for that, it can make the entire show pretty unstable, right? Because you were highly sensitive to the variance when you sample then afterwards, right? So then the idea is make a cut here, right? We don't spend a network layer here. We can just, for example, in Torch, you can just register a set of parameters you can learn, because what happens then, you can make initial conditions a bit larger, so your agent explores basically much better at the very beginning, but it learns to decrease the variance of its actions, right? So over time, your distribution just narrows down more or less to the mean value of the policy. That's the idea. That's easier to implement, and it's much more stable to do, right? But important, you need to have, you should have, we cannot just cut it completely and just work with the mean value, but also work, makes it somehow more or less deterministic already. But you could just need to spend some parameter you can learn, because once you can learn this parameter, you have it basically represented in the total loss, and if you backpropagate, you basically can optimize for these values. Yes, please.
What you explained reminds me in a weird way of Bayesian statistics. Does it have any relation to that? If yes, does it mean there is also a p-value involved of how confident I am that I found some probabilistic distribution, or am I just too tired?
No, because I'm tired too, so that's not a problem. I'm pretty sure there is analysis present. I can't give you it right now, honestly. I haven't thought about it. I mean, that's anyway something, you are happy usually with if the agent works, right? I mean, how much you really can rely what it learns, in statistical measures. I mean, people just have to run experiments and to cross correlation, whatever, and get some statistical measure out of it. But yeah, honestly, you got me a bit on the wrong foot with this question, but it's definitely a point considering. You maybe have something.
No, but you mentioned that it's a maximum likelihood estimate.
Yes, the estimator.
It's not directly Bayesian, I would say. It's really more estimating the.
Yeah, I mean, the problem is how do you need to define a proper prior distributions, right? How you can do that? That's the point, right? Because if you would know the prior already, that would improve a lot. But in that particular case,
so it's not okay. It's not.
No, not really. But maybe there is someone, and please enlighten me if there is work going on. I really want to have a look into it.
Yeah, there are algorithms out there which calculate the posterior probability, which use Bayesian approaches.
Yeah, if you really if you want to optimize for the if you want to optimize, it's different because then you basically want to try to calculate the mean over your posterior distribution for inference, right? But we wanted to figure out this distribution which basically gives us the best action. I'm pretty sure there's someone already doing stuff like that, but I'm not quite aware right now. Sorry for that.
So what does the ground truth look like for this distribution, for example?
Pardon?
So how does the ground truth look like for this distribution? Because if I want to do backpropagation, I need some ground truth.
No, you don't need the ground truth in that it's the wrong direction. So because you always, and this is your objective, you always want to maximize the expected return, That's the objective. Thing is, the equations look like that. That's the point, right? It's not said you don't have a regression task in there, really. That's not. But in the end, it looks like, the solution looks like, this is something very similar you get if you run maximum likelihood, scaled with some, measure of success, I would say. All right. So question is, can we replace the Monte Carlo target? And actually, yeah, we can do that. And good thing is also if you calculate expectations over something you want to replace, because this makes it much smoother in that particular case. And here we can just note, okay, we know that our Q function looks pretty similar. We just take the expectation and condition it on the states and actions, right? And we can do this even better if you say, okay, we take our Q function, and there's one fundamental principle. You can do this baselining approach where you can just subtract the baseline from the return. It will not change the result. And that's what we do here. So we have the Q function, and then we subtract as baseline the value function. And this gives us the advantage function, which is a very, very nice thing to have because it's centered around 0. And it gives you positive, negative feedback. Positive if your policy is improving, negative if you're failing to solve. That's basically. And what people do then here is basically they estimate the advantage function basically again with the TD error, right? This is what happens in here. So you can just rely on that basically because here you have just the Bellman principle again, and what you end up finally is you take your loss contribution basically and take this value estimate for the target, right? And for that you spend a second neural network because then you have a second function approximator. You want to regress then basically using the bootstrapping idea. You want to regress on the value of the states. And that's basically the idea of an actor critic, of an advantage actor critic. So, and this will basically serve as the constitution for tomorrow when Marius is talking about PPO, which is basically a way of making advantage actor critics learn faster. All right, so that's a bit reinforcement learning. We cut it here. I did my challenge, so I introduced it, so Marius can take over tomorrow. That's fine. Second, now we have still this guy sitting here, right? So you have someone connect to him, and therefore I just briefly want to talk about optimal control. And I studied mechatronics basically, and I learned all this stuff over there. And when I first got into reinforcement learning, I just figured, weird, it sounds familiar, but it's the wrong direction. It's like we're minimizing costs over there, otherwise we're maximizing rewards. And actually, there's really a lot of common in the concept of both, right? So let's switch over to the domain of optimal control. We say, okay, our states are generally continuous states, right? We have, that's something. Our actions, basically, it must not be discrete time. No, it's discrete time, sorry, it's discrete time, but it can be continuous actions in discrete time regime. So we can switch over the actions to these are the inputs, basically, you calculate when you calculate your controller. And we change the terminal for the policy. Policy is no longer a distribution. We make it deterministic, although there are concepts where you can work with stochastic controllers in optimal control, but I will not touch that. That's far beyond my understanding. And so we have a controller function, which is basically takes the states and the time. And then we say, okay, we know already state transition functions, these distributions. We change this over to differential equations. That's basically because we say it's deterministic, and we have dynamic systems involved. Therefore, we want to control these dynamic systems. All right, and then we say reward is turned to costs, and therefore we distinguish between running costs and terminal costs in the concept, right? But apart from that, pretty much the same, I would say, right? All right, so how can you derive the equations out of that? It looks like a bit too much math, but we'll see it's very easy to understand. So, okay, we have first, we are looking for the optimal controller, so we optimize for U, right? And for that, such a way that this functional, over there, this function of the costs is minimized. So it's just this functional of the running costs plus the terminal costs, right? We want this as low as possible, right? And no surprising, we can define a value function for that, right? And this is pretty much the same concept we had before. Apart from the fact now we really, we treat the time as a continuum. That's the difference, right? Before we had discrete time steps, we do the actions. Now we have the time as a continuum. And now how we can solve this, basically what Cass said before, we take the same trick, so we split up the value function into parts again. So we have the value function up to a very small time step, right? Plus the rest till I reach the end of the episode, or infinity if it's an infinite horizon case. But we can always split up the value function at some point in time. We can always split it up in two parts. That works. Okay, taking this, this guy, the remaining part is a bit annoying to solve the equation, so we make a simplification over here. We just take this guy and we develop a Taylor expansion around it, right? And we develop it around t. So it's easy. Then we can take the same equation, we plug it back, again what we had before, right? We can subtract, I show this back here, sorry. So we can subtract then here the value function on both sides, works. So we have this 0 is the minimum over the function of the costs plus the partial derivatives of the states times, very important, state dynamics, plus the partial derivative with respect to time. Okay, and now we just make a approximation because we say this integral is a bit annoying, hampers a bit, to get the nice equations. So we just approximate and say, okay, usually we run controllers pretty fast. So these time steps are pretty small. So this integral is approximately the costs times this time step. And since we have divided it by the time steps, we can rely to this equation. And this is called the Hamiltonian-Jacobi-Bellman equation. And this is a very important fundamental equation. Basically, if you manage to solve this equation, you can derive the optimal control policy out of it. It's basically, it's the expansion to the continuous time case. But there's a but. This is a partial derivative equation, and it's usually a pretty hard nut to crack. So you can hardly just solve this over here. But you can make assumptions, and this is the last slides I have now, I guess 4 slides. It just shows you 2 very prominent, important results out of this equation, right? So first equation, we call it the infinite horizon linear quadratic regulator. So why is it called that way? First time, we assume we have time invariant. It's important, it must be time invariant. And linear state dynamics, right? We say, okay, we have a linear controller, so the controller is just the matrix K times the states. Of course, it must be state dependent. And we say we have quadratic cost here. So we have the running cost looks like that. So you have a quadratic cost term on the states, and you have a quadratic cost term on the control itself, right? And in order to get these equations solved, the matrices Q and R must be positive definite. That's most important, because you really want to shrink down. That's the important point. Okay, just plug this in the equation right before, and there's one assumption we need to make here, that our value function has also a quadratic form, right? This is important, but you can if you're really interested into, you can show this by just plugging the controller in and running a Lyapunov analysis on your problem, and then you will see it is exactly in that form, and P has also the properties that is positive definite. That's very important. Okay, we plug this in our equation. Easy to just derive it because we know upfront that the value function has a quadratic form, and we take this everything, differentiate, resolve it with respect to u, and we see the relationship for our controller. So it's dependent on the cost, on the controller itself. This is no surprise at all, and of course on the input scaling. Plus, it depends on the final cost, right? This is the point, because in P you have somehow the final cost embedded. All right, we solve this, and this must be always true. This equation, the first equation there. So for every state, the expression in the brackets basically needs to vanish. So you just need to consider the matrix equation there, and you see, and this is a very, very important equation in a lot of disciplines, because this is a Riccati algebraic equation, and for that we have a solver. You have just SciPy, you have to have a Riccati solver, plug it in there, press enter, and it will reveal the optimal matrices for the controller. Right, so this is the first part. Maybe this was the infinite horizon, because it's sometimes inconvenient if I have to wait infinitely long until my controller reaches basically the objective. What can I do if I have a finite horizon case? It's basically similar. So we have in that particular case now we have a terminal cost. This is something we hadn't before, because it makes no sense to define terminal cost on an infinite horizon. You will never reach it anyway. So, but in that particular case, we have a terminal cost. It's also quadratic, and we see in that particular case also that the value function is again a quadratic function, but now the matrix P is explicitly dependent on the time, right? So basically your costs, the more the time progresses, your costs basically, your final costs basically shrunk down accordingly. Okay, we take this equation, just plug it in the Hamiltonian equation again, and you see nearly the same expression, apart from the fact that we have this part here, which is basically just due to the fact that we have this finite horizon case now, because we know upfront that the matrix P is explicitly dependent on time. All right, we do the very same like before. We take this, we stuff this back. We see, okay, this must vanish somehow. We can just concentrate on the matrix equation inside, and here you see what's again a very important and prominent equation, because this is now a Riccati differential equation. You need to solve this basically backwards in time, because you have a terminal condition. The terminal condition is basically determined by your terminal cost. All right, so I think this was my last slide. Yeah, it was my last slide. Yes, sure.
As I have no experience in like control theory, how restrictive is this like quadratic cost assumption?
It's easy. For example, if you have, usually you want to punish the energy you bring into the system, right? For example, you have a humanoid robot, basically just walking. You want the momentum basically, punished in the joints, because otherwise the robot would just very, very fast wear down, right? So therefore, you have already a quadratic term. You can just punish, the efforts you apply, basically.
Does a lot of effort go into forming a cost function that then is okay, but is quadratic? Is that like a big thing? If I have some control problem, do I put a lot of effort in to make it quadratic because this really helps me, or there are like alternative methods if it's not quadratic?
I mean, if it's not quadratic, there are alternative methods, and Simon will talk about model predictive control. I guess you will talk about, yes. So where we say, okay, my system dynamics is not really linear, because this is really, what you can do. Otherwise, you try to linearize your system dynamics, so you can take the linear control again. On the other hand, if it's strict, heavily nonlinear, you always have to do some linearization anyways if you derive these equations. But if you run model predictive control, you really try to plug in the real system dynamics and just optimize on the prediction. You basically have then a planning algorithm where you have a second step where you can correct your planned trajectory with the real observations you make, right? So in every time step, you basically make the predictions to some horizon, basically, but you just execute the very first action, or the first, and the next time step you make the very same, and this helps you narrow the problem down to the point where you say, okay, I have a clue how the problem will evolve, but I just, for the control purpose, I just take the most likely one.
But I would say having a quadratic form for a cost is nothing stupid to have in general. It's a very good combination.
Yeah, exactly. Because it comes, this entire stuff comes, you have strong relationship with this Bellman stuff, with this Lyapunov theory, right, which is a very powerful tool. And there you also seek for, quadratic forms, positive. If you find a value function which is of quadratic form and positive definite, your system is guaranteed to be stable, right? You can bring it to basically every state. And this is very, very desirable to have.
It gives very nice theoretical properties. You can study the properties very well because of its convexity. Yeah. And also, what you were referring to the non-linearity of the dynamics, what you can do is you take this approach, assuming linear dynamics and quadratic costs, and then you apply it iteratively. So it's an ILQR. Because you
Yes, exactly.
Quadratic control, ILQR.
Yes.
And it's like a Newton method.
It's linear to this amount of time.
Yes.
Although it's non-linear, you approximate.
I mean, there's a lot. There's a lot of work going on also in the model-based. I mean, the border between is vanishing, I would say. When do we talk about reinforcement learning or model-based reinforcement learning? It's mostly when we also learn the environment, because we need the environment basically for prediction, right? And you have to basically, in this model-based case, you have an outer loop, right, where you try to sample and to learn from your experience the environment, and then you have an inner planar loop, basically, where you apply iterative LQR or differential dynamic programming or stuff like that. I mean, there are people that also try to optimize on policies directly in there. So the Berkeley has a lot of interesting work going in there. And the reason is why you should do that, because, I told you this sample efficiency problem, and especially every model-free algorithm has a terrible sample efficiency, right? So you cannot really learn or train on robots in the field with with a model-free algorithm because it's worn down before the policy starts to converge, right? That's the point. So this model-based stuff is much more sample efficient, but, and there is a but, it's much harder to get it work. That's
exactly. We'll see for the advanced people tomorrow how hard it is to make something like this work. So for those who are interested in model-based reinforcement, there will be an advanced part where you learn this directly, hopefully, in the tutorial.
All right, so for the online audience, I think that concludes it basically regarding talks today. We will have now a tutorial session afterwards, which we'll do offline. I have to apologize because as I realized there is some breakup in the audio. Yeah, sorry for that. Take care.
Thanks a lot.
Thank you. All right, so be in touch. When does the session tomorrow start? I guess 9 something. Yeah. So basically, lectures will be concluded at 9 o'clock. Bye.
You can come